Yes,
Thank you.
I remembered. Okay, you're all off the hook. Take my shoes off. Get everybody get nice and relaxed. So I don't hear a lot of chatter out there.
Good morning.
Morning.
We've got almost 50 people here, and I hear hardly
Oh,
any
really?
chatter. Hi,
50
everybody.
people. Good
Well, I
morning.
think most of us are staying muted because we're
Mhm.
supposed to be in class.
Yes, the class doesn't start for 3 minutes.
I could be unmuted, but I have parrots and they like to talk. So
What do they say?
nothing intelligible.
Okay, so I have some friends and they were taught to say inappropriate things, the parrots.
No, they hear people in the room and they go, "You're not talking. You must be talking to us." So yeah, they engage.
Yeah. Yeah, and you know, it's remarkable how accurately they mimic somebody saying a cuss word.
Well, I'll say good morning from St. Louis, Missouri.
Good morning.
Good morning.
Morning.
Good
Okay.
morning from Oregon. I've got two teenage girls on this with me, so our videos and audio will probably be muted quite a bit so we don't overload the bandwidth.
Okay. How old?
12 and 14.
Oh, that's a good age. And you know, girls in radio. You know, I'm going to say something that does anyone remember ham radio from 40 years ago, 50 years
Yes.
ago, right?
Yep.
A bunch of old guys sitting in their basements. Well, those old guys sitting in their basements in the 1950s were young kids sitting in their basements, mostly boys sitting in their basements on the radio. They became old guys sitting in the radio. But I will tell you that even though one thinks of ham radio as being 90% men, 50% of the people who I teach in classes, 50% of the people I see joining our radio club here in Oregon are women, which is great. There's no reason it shouldn't be that way, and it's finally turning, the tide is finally changing. So I'm very happy about that.
When I'm listening to the different nets around the country, whenever I'm tuning in, I hear a lot of women call signs as well, calling out more so than men as of late.
Yeah, isn't it cool? We've got literally 50% here in Oregon, which is really nice to see.
We have much to thank for getting us all on here today. He's got his general. He goes, "You guys should really get your licenses. You should get your tech."
Yeah.
And finally, we're like, "All right, we're off for the winter break, so let's go ahead." And then we found out about this class, and we're like, "Okay, let's do it." Here we are.
Well, that was kind of my goal because I figured I needed a vacation. So I took off this week, and this is how I spend part of my vacation.
Thanks again, Scott, for doing this.
Does that make me a little sick in the head? Maybe.
Thank you.
Well, we're grateful for it for sure.
Thank you.
Yeah, thanks for teaching the class.
Yeah. It makes me a little sick in the head, probably. Okay.
Do they have Radioaholics Anonymous?
No, they don't. They don't. They're just called DXers and you know.
I think it would be great for our budget books.
Yeah. All right. Well, it is 9 o'clock. So let's start this thing. My name is Scott. My call sign is N7JI. I live in Eugene, Oregon. I've had my license since I was 15. I'm 50, almost 55. So I'm coming up on 39, 40 years of being licensed. All but 2 years, which were really the first year and a half of that, I've been really active the entire time. Gotten me through high school, college, work, family, lots of friends all over the world. You'll get to hear something about that. It's a hobby and a service rolled up into one that gives you lots of opportunity, as you've probably seen, to do community service, to volunteer for various different causes. It's something that is what I consider to be a complementary hobby to a lot of other hobbies. Like if you're into backpacking or hiking or mountain biking, or um, let's say you enjoy off-roading. I know that we have a large number of people who go off-roading way out in the woods, way out in the desert where there aren't any cell phones, because why would anybody put a cell phone tower there when there's basically no people? So it's a very complementary hobby in that regard. It's also a portable hobby. I tend to take it most everywhere I go. I travel all over the world with work, and I take a small station with me, and I see what I can do with the small station. And very often I go and find a group of local hams, and I go operate with them. Give somebody a phone call, say, "Hey, you doing anything this weekend for that contest?" "Oh yeah, we are." Well, so I somehow managed, for instance, to score myself a visit to OH5Z, which is a contest club in Finland, when I was there about a month ago, and got to participate with them in setting the Finnish national record in CQ Worldwide CW, which was an amazing thing. I was there for about 4 hours. I was on the air there for about 4 hours out of the 48 that they were there, but it turned out that I actually filled in and gave somebody a much needed break so that he could take a nap. So, because it was 48 hours straight. So, anyway, that's a little bit about me. I guess I can say I'm also, this is probably the 35th class that I've done in the last 7 years or so. I also teach Morse code. I also use Morse code. I'm on the air a lot. I am a DXer. I very much enjoy trying to do as much distance wise as I can, with as little power as possible. I'm also ARRL's Oregon section manager, and that's something that I was appointed to in September. So a lot of the management stuff from the American Radio Relay League for the state of Oregon kind of falls into my lap, which actually turns out I really like doing that. So I've helped to start a couple of high school clubs here in Oregon. I helped to start the U of O radio club over at University of Oregon. I started a museum station here in Eugene at the Eugene Science Center. And after 10 years, we basically have people coming into the Eugene Science Center, and whether they know there's a station there or not, we help to get them on the air. We let them experience what radio is. And I think in the last year, we've had 4,000 people on the air from the museum station.
Wow.
That's remarkable.
Yeah, it's a lot of fun. The interesting thing is you can go as far as you want with this. If you don't want to spend much time doing it, you just want to get a technician license and throw the radio in the drawer. I hate to say it, but that's your loss. There's as much to do in this hobby as you want to do. And I mean, in 40 years, I would say that I've scratched the surface of all the things that can be done. So, all right. Well, you guys ready to start?
Yes.
So the first thing we're going to do is we're going to say, okay, well, we're going to share this screen. And the first thing we're going to do is not go through the book in order. Okay, so does anyone recognize this picture?
Wavelength.
That is the electromagnetic spectrum. And the first thing I'm going to say is that visible light, notice it's all the way there on the right. Everyone probably recognizes Roy G. Biv if you ever look up at a rainbow. Those are the different colors of visible light. So what I'm going to tell you right now is you're going to have to believe me for now that visible light is a form of electromagnetic radiation. That means it has an electric component and a magnetic component. Those will make more sense in a little while. And that the only thing making these waves, making these frequencies different from each other is how much space they take up. how many times they repeat every second. So red, notice red through purple, Roy G. Biv. Those are very, very short waves, but you get a little shorter than that off to the right, and you get into this thing called ultraviolet. Beyond that, you get into X-rays. If you go to the left of red, you get to infrared, which is IR. You go longer and longer and longer, and then you get to this thing called radio waves. Radio waves are all the waves that are longer in wavelength and lower in frequency than infrared. They are all called radio. So what we're going to do now is we're going to start doing some drawing. Okay. So I know you probably didn't think this was a math class. This is actually a math class. So what we're going to start with is this line. I'm going to erase that. And we're going to draw okay. We're going to draw this thing called a circle. Okay. So for those of you who haven't been in trig, you're learning something new. For those of you who took trig 60 years ago, we're going back to something that you learned 60 years ago.
Yeah.
Maybe you haven't touched it since then, but it's hopefully going to make sense today. Okay. How many degrees are there in a circle, everyone?
360.
360 degrees in a circle. Okay. 360 degrees in a circle. Let me make sure I can get this. There we go. That's a bit better. 360 degrees. Go with the darker. Oh, it's a fading ink. I don't like that. Let's go with a thicker width. Okay, 360 degrees in a circle. And by definition, our 0 degree mark is right over here on the right-hand side. And the way that it works is that we wrap around that way, counterclockwise, until we get to 90 degrees. Oh, man, that wasn't intentional. Sorry, brand new pencil, brand new app. We're gonna 90 degrees. Okay, there's 90 degrees. And then we're gonna keep going around until we get to the left-hand side. We're gonna get to 180. And then we're gonna keep going around until we get to, I'll pick a different color, 270 degrees. You know what? I don't like that yellow. Let's use something other than yellow. There we go. 180 degrees. Okay. So as we go around this circle, that point all the way on the right-hand side has two names, doesn't it? It has 0 degrees and it also has 360 degrees. Well, considering that a circle as we go around this way continues around and around and around, can you think of another name for this point all the way on the right-hand side? Zero degrees and 360. Can you think of another name?
No. Home.
Home position, origin, yeah. Another name is 720 degrees. Because we went around twice. Could we go around 3 times?
Oh.
Could be 1080. We could have also decided that instead we're going to go the other way, in which case it would be minus 360. We could have gone around the other way twice, in which case it's negative 720. So this point, and in fact, every point on a circle, because it goes around and around and around, really has an infinite number of names that describe it, which is actually very useful because that means that if we now take this, and we're going to do a little bit of erasure here. of all those names, we're going to do a plot over here of, we're going to look at how far up. This is by definition called the x-axis, and this is called the y-axis. We want to know how far above the x-axis, which is the horizontal axis, we are at any given point. Well, I would say that if we have a unit circle and say we have a radius of 1, then we're going to get to a maximum of +1 and a minimum of -1, which means we're 1 unit underground. So we could draw this and we'd say here's our 1 and here's our -1. And when we're at the 0 point, that's a point of interest. We're going to call this our 0. When we're at the 0 right there, how far above or below are we? And I like these classes to be interactive. So feel free to let me know. How far above or below the axis are we? We are right on the axis. So we're at 0. All right. How about when we're at the red point, which says 90?
We're at 1.
We're at 1. So we're going to put it up here. How about when we're at the blue point, which says 180?
Is that 2?
It's back at 0.
0.
Right? Because we're over here on the left-hand side. We're flat on the horizontal axis. So here's the 180 point. And then when we get down to the purple point, we're at 270. And when we get to that point, we're down here 1 unit below. And then we get back to the green point, which says 360. And we're going to put a 360 mark right here. And we're back here. And now we connect the dots. And we should form a pretty cool shape. Anyone know what this is called?
Sine wave.
That's a sine wave. Yes. That's a sine wave. Okay. Now, let us say that we were to continue with this and keep going. We could actually continue to draw this back this way and this way. So let's say that instead we decided that we were going to start right here. And we were going to end over here on the right-hand side. That would be a cosine, which is how far on the x-axis we are. Now, it doesn't really matter which one we're looking at because they're really just versions of the same thing. So a sine and a cosine are basically just shifted versions of the same thing. This is something that is made when a thing, we'll call it a particle or a person on a merry-go-round, is going around and around and around on the merry-go. This is how far away from one axis they are in per unit time. So now the next question that I have is, because this shape goes on forever, does it matter if we look at a spacing? I'm going to use pink over here. Does it matter if we use a zone over here to look at the same function? What is that called? Right here on the left.
Sine wave.
Still a sine wave. Yeah, it's still a sine wave. It's moved. It's in a different place, but it's still a sine wave. So long as you go ahead.
A cycle?
Yeah, that's what, and actually this is one cycle of that sine wave. So now what we're going to introduce, now that we've gotten the concept of what a wave looks like, if we move this wave and we take it from a different point, this is called a phase. So I'm going to start with a new screen because I can, and we're going to draw the circle again. Here's our circle, and here's our wave. There's our wave. Okay. Now, we're going to say, for argument's sake, that this starts at 0 degrees. Now, I'm going to draw another wave that looks just like this one, but isn't like this one.
Hey, Scott, if you started a new screen, I'm still seeing your old one. Is everybody else seeing that?
No, I'm seeing his new one.
I'm seeing it. Oh, there it is. It just popped up for
Okay.
me. Okay.
Just
I
a
may be
little
having
delayed.
bandwidth issues. I'll stop my video.
Okay. Okay, so if this is 180 degrees and this is 360, well, then this right here is the 90-degree mark. So what we have here is two identical sine waves that are separated by something called a phase shift. The phase of an angle, or the phase of a function, is how far shifted from something else it is. And it's measured usually in degrees. So in this case, we could say that our our orange curve is delayed by 90 degrees. It has a phase angle 90 degrees, a phase delay of 90 degrees compared to the red one. Okay, so now we have angle, we have phase, we have sine wave. Okay, so now we're going to draw our circle again. And what we're going to do now is we're going to take our circle and we're going to turn it sideways. So we're going to very slowly rotate it so that we're looking at the edge of the circle. So it's turned sideways. So as this thing, well, you know, person on a merry-go-round or a particle on a circle goes around and around, if we rotate that picture so that we're looking at it from the edge, what are we going to see? What is that particle going to do?
Go up and down.
It's just going to go up and down. Exactly. So as we, oh, you know, I just thought of that. I have a really cool, I have a really cool use for this erasing pen. Here we go. Ready? You start here and we go up and we go down, and I hope it erases. Oh, great. Now it's not erasing. Oh, now it's erasing. Okay. So we go up, and now we go down, and now we go up, and then it goes down, and then it goes up. Ah, there we go. Cool new tool. And then we go up, and then we go down. So basically what we see is the particle moving up and down. Why this is useful is now we're going to take this thing that's spinning around and we're going to move it in time so that we have this thing that is now just tracing an up and down path, and we're going to move this way. Okay, so now we have two things happening. We're going to go back up to the circle right up here, and we're going to say, okay, well, how long does it take for this particle to make one full trip around? If that's a person on the Earth, how long is that to go around the sun?
24 hours.
It's not 24 hours. If it's a person on the Earth going around the sun.
365 days.
365 days.
365 days.
If it's a person standing on the surface of the Earth, it's going around the center of the Earth, it's 24 hours. Right? If it's us going around the center of the Milky Way, it's more like 200,000 years. If it's an atom and we have an electron essentially making which is not exactly circular, but if we have an atom with an electron going around the nucleus, this could be 100 trillion times every second. So clearly these are very different things. The amount of time that it takes to go around the thing that it's orbiting is known as t, which is the period. So that could be 3 seconds. What would happen if I was on this merry-go-round and it went around once per second other than having to vomit off the side of it? What would my period be? If it went around once per second, what would my period be? Would be 1 second.
Equals
Exactly.
1.
Right. If I went to 3 seconds, what would my period be?
T equals 3.
Okay, and I'd be somewhat less likely to puke off the side of it. What if it was 30 seconds?
30 seconds.
It would be 30 seconds. Okay, now the question is, if I have a period equals, let's say, 3 seconds, how many times per second would I go around?
Three.
So I'm gonna say t is 1 second. T is equal to 10 seconds. Okay. So if I went around and it took me 1 second, I could divide 1 by the period, and I would get this thing called 1/3, or 1/3 seconds. This is known as my frequency. How often I am doing this. I am going around 1/3 of a rotation per second. Frequency is measured in per second. That is the unit of frequency, per second. That has a name. That's known as a hertz. So let's say that I have a frequency, let's say I have a period of 5 seconds.
Star.
So let's say I have a period of 5 seconds. What would my frequency be?
1/5.
1/5 of a second. 1/5 per second. Remember, the
Stop.
units is 1 per second, which is equal to 0.2. And the units again is per second, which is also known as a hertz. Okay, so now let's instead take this and we're going to change this to a frequency of 100 hertz. Oops. Or 100 hertz. What does 100 hertz mean? How many times per second? It means 100
100 times.
per second, 100 times per second. So now, what would the period be? How long would it take me to make one full orbit?
Scott, I've heard 2 different people call out for you.
Oh.
Who needed Scott's attention?
I thought it was just random noise.
That might have been.
Yeah, if you're quieting a dog or something, you know. So, time and frequency are inverse, which is 1/100, which is 0.01 seconds, because that's a unit of second. So, for a frequency of 100 hertz, my period is 0.01 second. I do not want to be on that merry-go-round. Okay. So the next thing we have is, again, we're going to draw this circle and we're going to be going around and around and around and around. And now we're going to take this and we're going to turn it on its side. So if we were to go around at a frequency of 1 hertz, that would mean that it would take 1 second to go around. If we were to look at this edge on, we would start in the middle and we'd go up, and then we go down, then we continue down, and then we go back up, and that time would take 1 second to make one full trip. So now what we're going to do is we're going to add the concept of this edge-on thing moving through space at a velocity v. And velocity is usually measured in meters per second. So we now have this thing, which is meters. A meter is a meter.
No.
There we go. A meter is, I believe, 1/10 millionth of the diameter of the Earth. And a meter is also about 39 inches, slightly longer than a yard. So we usually measure wavelengths in the MKS system, which is in meters. That's the units that we use. Time is time, so we use seconds, very convenient. So now as we are moving, as our rotating thing is moving, now instead of just our particle moving up and down, our particle is moving up and down on this plane, but now the whole plane is moving. And as it does this, it traces out a pattern that looks like this, which is once again, what do we call that?
Sine wave.
We call that a sine wave. Okay. But now what we've managed to do is to say, well, our whole thing is moving at a certain velocity in meters per second. And we know that we have a period. And from the period, we can also have a frequency. All right. Well, does everybody notice the seconds on the denominator in both of those? You notice that the frequency is in 1 per second and the velocity is in meters per second.
Yeah.
Well, guess what? Because we can do cool stuff, we are allowed to do cool stuff with math because math is awesome. Now, what we can do is we can say, well, we're going to just divide our velocity by our frequency. And we get meters per second divided by 1 per second. And the per seconds cancel out. And what do we get?
Meters.
We get meters. We get a physical length. This, we use the Greek letter lambda. This is known as R because we're looking at a wave right here. This is known as a wavelength. So we now have V is equal, we can rearrange this equation right here. V is equal to F lambda. And we basically now know that our frequency times our wavelength is our speed. We can do this for any kind of wave. So the first one we're going to do is we're going to do the speed of sound. So do we have any musicians here? Anyone play a guitar, wind instrument, anything like that?
Yes.
Yep. So do I. Okay. V is equal to F times lambda. Okay, we're going to pick a frequency of 440 hertz. Anyone who's ever tuned an instrument should know that's an A. And so now we're going to say that our velocity is 1100. Sorry, we're going to change that. We're going to use meters, 330 meters per second. That's our velocity. So the question is, as that A is traveling through air, because that velocity is the speed of sound through air, we are going to figure out how long the wave is as it travels through the air. So we're going to rearrange it. V is equal to F times lambda. Lambda is equal to V divided by F is equal to 330 divided by 440. And this is in meters per second. And this is in 1 per second because it's in frequency, which is hertz. Those cancel out. So our units are all right. And we get 0.75 meters. So that note of 440 hertz in air has a wavelength as it travels of about 0.75 meters. And if you were to look at the instrument that made it, you would probably see that for whatever reason, due to string tension or the length of the column, that it is related to that wavelength, either a half wave or a full wave long, which I think is pretty cool, because this basically allows us to relate things that we can see and feel to things that we can hear. So now what we're going to do is we're going to instead take that wave and we're going to say that our velocity is considerably higher. And the reason we're going to say it's higher is because now we're going to go back to this. Everyone remember what this is called again?
Wavelength.
It's the electromagnetic spectrum. It's the spectrum of all things electromagnetic. And every one of these waves has something in common. They all travel at what speed?
Speed of light.
Speed of light, which is
186,000 per second.
remember, we use meters, 300 million meters per second. That is approximately the speed of light, which is actually a nice, we're really lucky that it's even close to that because it makes the math pretty simple. So 300 million meters per second. That's our velocity. Well, remember we just calculated that formula. V is equal to F times lambda. Get used to this. F is the frequency. And that's measured in 1 per second, or things per second. Lambda is the wavelength measured in meters. So we multiply them together, we get meters per second, which is indeed the velocity. So we know we laid out our equation correctly. But now we're going to say that our speed of our wave is, instead of the speed of sound, we're going to say that it's 300 million meters per second. So we're going to do this math and we're going to say, okay, let's say we have a frequency of 1 hertz. So now lambda, as we rearrange this equation, is V divided by F is 300 million divided by 1. How long is that wave?
Wave.
300 million meters long, right? This is not a very practical thing to do. That's a really, really, really long wave. I mean, it's 300,000 kilometers long. That's a really big wave, right? And considering that antennas have to be a portion of a wave in order to make it work, this is really impractical. So what we're going to do instead is we're going to say, okay, let's use something a little closer to being useful. 300 million meters per second. And now, instead of 1 hertz, we're going to say that our new frequency is 3 million hertz. And what does that mean if it's 3 million hertz? That means that our thing going around is going around how many times per second?
1.
300 million.
3 million times per second. It's going around 3 million times per second, which seems like a lot until we do the math. And we find that V is equal to F times lambda. And lambda is equal to 300 million divided by 3 million, which is 100. Well, 100 meters. That's not too long. That's 330 feet. That's, that's the size of a soccer field, size of a football field. We're getting closer to something we can actually use, right? So now instead, we're going to replace that 3 million and we're going to say that it is 30 million. And now we're going to do our math again. And instead of microwave's done. Okay, so now what's 300 divided by 30, everyone?
10.
That is 10 meters. Okay, so now when we start looking at practical uses of radio waves, we get to something like this. And I'm going to bring up something on my screen if I can find it. Everybody has a copy of this. Here we go. We're going to share this as soon as I can find it. Sorry, it's a little slow. Here we go. Does everybody see that right there on the left-hand side?
Yeah.
Wow. Okay.
Yes.
So we are now at 10 meters. Wow. Okay. Well, 10 meters, as we know, it's approximately 28 million hertz, right? Up to roughly 30 million hertz, which we found was actually about true. And what it turns out is that these particular frequencies are actually useful to us. And in fact, you will notice that all of these different bands are measured in wavelengths as well as frequencies. The reason we do that is because our bands that we have access to as hams are known by the rough number of meters, the rough wavelength in meters that are associated with the wave that's being put out. Okay, so now, oops, stop there. Okay, so what we've basically now done is we have developed a relationship between this thing going around, which is a particle making a circular path. We rotated it on its side, and then we've decided that here's that thing that's on the circle that's on its side, and we've moved it this way. Now, the reason we do this is because, remember we said that those are electromagnetic waves that we deal with? Well, this is an electromagnetic wave. Everybody ready for this?
Yeah.
We have our electric field going this way, our magnetic field going this way, which is the letter H, and then our direction of motion that goes in this direction. And I think it would make more sense if I did this in a different color. So let's take advantage of the awesome colors that I now have. Those are perpendicular to each other and perpendicular to the direction of travel. So the electric field goes up and down. The magnetic field goes back and forth, and the whole wave moves in the direction of the letter S. This is how an electromagnetic wave travels. And if everybody wants to see how this works, the easiest way to describe it is you hold up your right hand, but don't do your left hand because then the math won't work. Take your thumb. Your thumb is the direction of the electric field going up and down. Your index finger is the magnetic field. These are always perpendicular. This is how electromagnetics works. They're always perpendicular. And then your middle finger is perpendicular to both of them. So E and H gives you your direction. So this basically means that if you hold up your three fingers, this is called the right hand rule. This is your electric field, this is your magnetic field, and this is your direction of movement. And that allows you to figure out which direction your energy is traveling through space. So now
that's very cool.
Yeah. Now here's the next question. What does sound have to travel through?
Air.
Air or other things?
Solids.
Solids, liquids, right? Okay. How about electromagnetic waves? There used to be something that was theorized that was called the ether. Anyone ever heard of Ethernet?
Yes.
The Ethernet,
Oh, yeah.
the Ethernet is called Ethernet because at one point it was theorized that electromagnetic waves had to have some kind of medium to travel through, which was called the ether. Well, it turns out that electromagnetic waves, which is fortunate for us, don't need anything to travel through. They actually travel through empty space quite nicely. And why are we fortunate about that? Come on, somebody tell me why we're fortunate.
Don't
It
have
means
anything interfering.
Well, no, we're fortunate about it because sunlight would never make it to the earth. If it actually needed something to travel through, That's all that sunlight that was emitted would never make it to Earth, and we would not be here. So, all right. Well, that's your basic treatise on electromagnetics. And I'm sure there are some questions, and maybe it's a good time to ask if anyone's got questions on that. And remember, there are no dumb questions. And if you're thinking it, that means that half a dozen other people are thinking it too.
I have a question.
Yep.
So if you have current moving through a dipole, is what direction is the electric field in relationship to that dipole? So does it go along with it and like linearly, and then the magnetic
electric field follows in the direction of the motion of electrons in the wire.
Okay.
So the electric field is parallel to the wire.
Okay. Cool.
And the magnetic field goes around in a loop. So as electrons, we haven't gotten to electrons yet. So we will, though. We will.
I have a question, Scott.
Yeah.
So thanks for the insight that an orbiting object traveling through space would create this sine wave. And I'm curious then about, I think the concept is polarization. Mm-hmm. So you've drawn these as going kind of up and down.
Yeah.
Do they go, it sounds like with the electromagnetic and electric fields being opposite, they go kind of around that center spot and move like move through space like a corkscrew instead of kind of up and down. Is that
actually, if you have just, if you look at your electric field and you don't, the question is whether or not you rotate them. And if you just have the circle going around and you turn the circle perpendicular, one is always going up and down. And the other one is always going back and forth and back and forth. Now, what you can also do is you can actually rotate the circle, and that causes something called circular polarization. So there's a whole bunch of things you can do with it.
So I'm hearing you say that most of the time the electromagnetic wave is going on either the electric or the magnetic axis, and looking like that sine wave. I've always thought about it as kind of a flat thing, as opposed to it's moving side to side as well on both electric and magnetic at the same time.
You know, it really depends how it's drawn and how the waves are generated.
Okay. Cool. Thank you.
I mean, so if you were to draw, for instance, and we're going to get to this because now that we've established what a wave is, we have to figure out how to actually make it and how to use it. So here's a piece of wire, and we're going to get into the physics of doing this in a little bit. As you have a piece of wire is made of metal. Metal is made of atoms. Here's your nucleus. I guess we're doing physics now. And you have electrons flying around in orbits. And so here are your electrons. And these are your positive charges in the nucleus, and your electrons are negative charges. These are also very tiny and moving very fast. What makes an atom good at conducting electricity? Electricity is the flow of electrons from one point to another. So what makes an atom good at being a conductor of electricity is that if you put an electron in over here, it will exceed the number of electrons that the atom can typically hold. So let's take, we'll take copper, which has 29 protons and 29 electrons. Well, some of those electrons that are in the very, very far reaches compared to the nucleus are kind of loosely held. So what happens is, as an electron drifts in, another one pops out. Well, electrons are essentially identical except for quantum spin and stuff like that, which we're not going to get into because it doesn't really apply here. As we move another electron in, we get another electron that comes out. If we put 3 electrons in, we get 3 electrons out. Well, that to me, if this becomes a black box and you don't know what it is, if you put an electron in, you get an electron out. This is known as a current. Did we have to push very hard? No, right? You just drop an electron in and another one pops out. This is a conductor of electron, conductor of electrical energy. The amount that I have to push right here into this box, the degree to which I have to push is known as the voltage. And the amount of fight that this thing puts up inside the box to that push, this is known as resistance. So for a conductor, conductors have very low resistance, which is why we use them. When you push an electron in, another one comes out the other side. When you have a high resistance, you might have to push really hard and maybe you'll get one out the other side. So that being said, we have now actually gone into the physics side of things. I could tell you where this is in the book, but honestly, I don't exactly remember. Let me see. Let's see. Electrical principles. Okay, so we're now into, I guess, what would be page
4.
Page 4. Okay. All right. So we're right at the beginning of the book. So I jumped, and like I said, one thing I do is I teach, I do the waves first, but now we're into how you actually make them. So here's our black box with a thing in it. If I have to push really hard, the voltage, which is the push, and the resistance, which is how far it has to fight.
Hey, Scott.
Yes.
I just got called into work, so I'm going to be
saw
listening on my phone.
Yep.
When will you be sharing the recording? That way I can just review what you're drawing out.
It'll hopefully be by 2 o'clock.
Okay, cool.
All right. Sorry, man.
Hey, don't be sorry. I'm still listening on my phone, but
oh, that's good.
Work is work.
Yep. Okay. So let's see. Voltage is the amount of push. That's measured in volts. Resistance is measured in ohms, which is the amount of fight that something puts back, something pushes back with. And current is the letter I. And this is actually from French, which is why current is represented by the letter I. So now what we're going to do is we're going to squeeze that box down into a little piece of nothing. And we're going to make it look like this. Now we have a whole bunch of these little atoms that are squeezed down into what we know as a wire. And so we're going to push with a voltage V. This is how hard we push our electrons. We're going to try to stuff electrons, which have a negative charge, into this wire. And the wire is going to fight back with a resistance, which is measured in ohms, named after Georg Simon Ohm. We're going to push with a voltage. This is also known as EMF, which is electromotive force. Basically, it's a force needed to cause electron movement, EM. So electromotive force. And this causes a flow of electrons. This is known as a current, kind of like the current in a river, the current in a stream. This is measured in amperes. And it's represented by the letter I. So there we go. We now have a voltage. Sometimes this can be represented by the letter E, either V or E. It's measured in volts. We also have our current up here, and we have our resistance, which is our ohms. These are related by this formula. Has anyone ever seen this before? I hope.
Oh, yeah.
Yes.
E equals I times R. also known as Ohm's law. And actually, this is the first half of Ohm's law. So E equals I times R. So a very simple application of this, we're going to draw a battery, which is an electromotive force in a box. And we're going to say that this battery has a push or electromotive force of 10 volts. And we're going to draw a resistor. A resistor is a device that is specifically designed to have a certain resistance, which is measured in ohms. So we're going to have E is equal to 10 volts. R is equal to 1 ohm. And the wire we're going to assume is perfect and doesn't have any resistance because now all the resistance is in the resistor. And now what we're going to end up with is, because we have a plus and a minus, our current flows like this and around here, back into here. As our current flows, what's going to get in the way of that current?
The resistor.
The resistor, right. The resistor quite literally resists. It resists the flow. And now we can do E equals I times R. We will sometimes draw this for the sake of class as this in a circle. If you can't remember which way to do it, or let's say you're not that good at algebra yet, and you have E equals I times R, we have our I. The I is the one that we don't know yet. We cross that out, and we're left with E divided by R. Okay, so we have E divided by R, which is 10 divided by 1, which is 10. And we're looking for current, so that's 10 amps. So that's our current flow through that resistor, limited by the size of the resistor and generated by that battery. So let's do another one. We're going to have a 6-volt battery. Anyone have any experience with 6-volt batteries and know what they're also known as if you go to the store and buy them? Is anyone old enough like me to remember?
Lantern battery.
A lantern battery. That's right. Yes, this is a lantern battery. Okay. A 6-volt battery. Okay. So now we're going to take this and we're going to have a 6 ohm resistor. Okay. And we still don't know our current. There's our current flow. We have E, I, R, like that. We draw our circle. We don't know our current. So our current is equal to E divided by R, right there. 6 over 6 is 1 amp. There we go. Our current is 1 amp. So we know that our current is 1 amp going through this circuit. And here's our plus and here's our minus. Okay, now, does anybody see a problem with this? We're just going to bring it up right now. Does anyone see a problem with any of this? What is current the measure of? What is current quite literally?
The flow of the current.
The flow of what?
Voltage.
Nope.
The current.
Electrons.
Electrons. The flow of electrons. What is the charge on an electron?
Negative.
It's negative. Okay. Does anybody see a problem with this? So here's our positive terminal of our battery. And we say that here's our resistor and our current goes like that. Does anybody see a problem with this?
Makes it go backwards.
It makes it go backwards. Yes. Okay. Now, this is something that happened about, let's say 175 years ago. And what happened at that point was that the electron had yet to be discovered. So it was assumed, because they found this thing called a battery, scientists found a thing called a battery, and they said, well, this is our plus terminal and this is our minus terminal. And we know that something's moving caused by this E and our R, and we know we're getting current. Oh, it must be going that way, because why wouldn't it go out of the plus? No one had discovered the electron yet, and no one knew it was negative. So here we are 170 years later. We know, in fact, that the electrons travel this way, from the negative to the positive. But to be frank, that doesn't really matter. And the reason it doesn't matter is because for 175 years, we've gotten it wrong. So we will continue to get it wrong as far as anyone here is concerned, as far as engineering school is concerned, as far as anyone is concerned. Current goes from plus to minus. And we also have something called a ground. A ground is right here and is measured as 0 volts. So it's true, the electrons flow from the minus to the plus, but current flows from the plus to the minus just because we have to deal with the mistake that was made. As they say, mistakes were made, and everybody knows that this is how it works, right? Even though they're wrong, and even though we're wrong, this is what we do. Okay, so now what we're going to do is one more thing. So what we're going to do here is we're going to draw this circuit again. And I kind of like that green color. And okay, so we have our voltage. Here's our E. And we're going to measure it in voltage, in volts. And it's going to be, let's say, 10 volts. And we're going to have our resistor, and it's going to be 1 ohm. And we go through our Ohm's law thing. And we say, okay, well, E, get used to drawing this, E-I-R. We don't know our current, so we cross that out. I is equal to 10 volts divided by 1 ohm is equal to 10 amps. Okay, now we have current flowing. We have 10 amps. That's actually an enormous number of electrons being moved. Well, so now the question that we have to ask is we have our current, which is 10 amps, and we have our voltage, which is 10 volts, and we have our resistor, which is 1 ohm. So we have another equation which proves very useful, which is Ohm's law, but it's a separate representation of it, and it utilizes the letter P. P as in power. This is measured in watts. And a watt is a rate of dissipation of energy. And there's something important about energy, which is that it can neither be created nor destroyed. It just changes form. So our power is measured in energy per unit time. And I don't want to use that. I want to use energy per unit time. That is power in watts. And actually, it turns out that energy is measured in a unit called J, which is joules. And it's also joules per second. So for electricity, P is equal to I times E. So now we can look at this equation, and we know that we have 10 amps, and we have 10 volts is equal to 100. And what are the units on that?
Watts.
Watts, which is equal to 100 joules of energy per second. Now, why is this useful? Because is there any difference between energy that is stored in a battery? This is a battery. Is there any difference between energy that's stored in a battery, or let's say that I take a golf ball and I hold it in my hand up here above the ground? Is there any difference at all?
You're talking about a capacitor, right?
No. I'm talking about actually holding this golf ball above the ground. What have I not done with that golf ball?
Let it
that
go.
I could do. I could drop it. That's right. That is potential energy. What's inside the battery? Battery is a chemical storage device that is able to deliver energy. This is also, before it's used, potential energy. Energy is basically, as I said, neither created nor destroyed. It just changes form. So if we were to use this potential energy in the golf ball, and I were to drop the golf ball, what would happen to the energy? What would it turn into?
Motion.
It would turn into motion, which is kinetic energy. And then how about when it hit the surface? What would happen to it?
Resistance?
Yeah, it would cause waves and noise to emanate from the surface, right? And if it was a perfectly elastic collision, if the golf ball didn't bounce, all the energy would be transferred to the surface. Similarly, if I have a battery and I go like this, and I use up that potential energy, where does the potential energy go? Has to go somewhere, right? Because we're doing work. We're using power because Ohm's law says so. So now where does the energy go?
Into heat?
Into heat. It turns into heat. So this resistor has to dissipate energy at that rate, 100 watts. Now, we also have a name for this. If we have designed this resistor to dissipate that much heat and we blow air over it, what is that called? That's known as a space heater. So by doing that, resistors basically burn up energy as heat. So a golf ball, when you drop it, that'll turn into sound, that'll turn into ripples, that'll turn into waves, it'll actually cause a little bit of heating. Electric energy, when it's burned up in a resistor, will turn into heat. Now, if let's say we replace that resistor with something else that converts that energy into radio frequency energy by virtue of causing a sine wave to be generated, we have taken our battery power, which is stored energy, and turned it into radio waves, which are traveling through space. The other thing we can do with it, of course, is that we can actually take an electric motor and we can hook it up to, we could hook up a battery to an electric motor and spin the motor around. So energy is one of those cool things because you can move it around, you can have it change shape and form and do all kinds of cool stuff with it, like lift things and move things, like, you know, have drive an electric car driving down the road really fast. That uses current. Everybody ready for a 10-minute break?
Oh yeah.
Yes.
Sure.
Think of all your questions because we want to hear your questions. Like I said, there's no such thing as a dumb question.
Hey, Scott,
Yeah.
what time is it where you're at?
10:05.
Okay.
What time is it there?
It is 12:05.
So Illinois,
My mistake.
Illinois, Texas,
Iowa.
Okay.
Yeah. That's why I was late. I thought it was a 3-hour difference.
So that's the first part of the exam.
The first part is clearing the clutter off my desk.
Yeah, okay. All right. Short break, and we'll see y'all in now 8 minutes. Okay, so while we're waiting for people to come back, does anyone have any questions that are just burning that they have to get out there? This is a good time to ask.
Yeah.
And it can be about the practical, the practical process of taking an exam, or pretty much anything. Don't be shy.
Yeah. So Scott, on the testing on Friday, how's that going to work? How would that?
Are you're signed up for it already?
Yeah, I'm signed up for it. Yes.
So what'll happen is that I will have a list of people to call. They will use me as the telephone guy, and starting at, I think, 10 o'clock our time.
Yeah.
We'll figure out who wants to go first, who wants to go last, et cetera, et cetera. It takes 3 examiners to give an exam. You have to be in we'll call it a sterile environment. It doesn't really have to be, but they'll check above on camera, they'll check below. You have to have 2 cameras, one on the computer and one looking from the side, looking at your hands and your face and the computer screen. So, and that's usually an iPhone or an iPad or an Android or whatever.
Mm-hmm.
So basically then we've got 2 cameras on you and at least 3 examiners in the room to give an exam. And it'll be done on the computer. If you've used hamstudy.org, it's the same site except a different version of it that generates FCC acceptable exams, I guess you'd say, vetted exams.
Yeah.
And it'll just generate a random exam from the question pool for you based on the number of questions from each section that have to be asked. So if you're worried, what if I get all math and I'm not good at math? That's not going to happen. If you've taken practice exams, you've probably seen that, oh, well, there's 3 or 4 math questions and that's it. And the reason there are 3 or 4 math questions and that's it is because that's all that's generated. That's all that the question pool requires you to do.
I might have missed that. Did we have to sign up for the test?
It's in the emails. There's something that you don't have. I mean, you can sign up for any test you want with anyone you want. We just have an exam session that was specifically set up by the Anchorage group for this class.
Right on. Yeah, I'll go find it. I appreciate all the communication you sent over email. That was awesome.
I know it's a little annoying sometimes, but
it wasn't annoying at all. I appreciate it. It's like, X amount of days and all that. I'm like, thanks for all the reminders.
Yeah.
You keep us all tracking.
Well, part of it is that I've been through I've been doing this for a long time now. The last time I took an exam, like for real, was 1987. Actually, 1986. That was the last time I took a licensing exam. But just to keep myself fresh, I actually do go through and take exams for practice to see what the question pool looks like. And I know that there's a lot of stuff in there. And if you try to go in cold, I've had people go in completely cold starting on, day 1 and taken a few practice exams and managed to pass their license exam. Wow. I've had it happen, but they're usually, an electrical engineer, and it's really just touch up at that point. If you don't have significant background in it, you can't expect that to work. So
right on.
So do we need a separate microphone? Can we do our headsets or no for the test?
No, actually no headsets allowed for the test.
So my mic isn't working.
Actually, it sounds fine right now.
Yeah, but I got my earbuds on.
It's just something you'll have to ask. They might be okay with it if that's all that works.
Okay, but I should really try to find something else to use.
I would, yeah.
Either get a new mic or something.
So So the group that gives the exams, of which I'm a part, we can I can have them come in. You can always send an email to Kent. Kent is the leader of the group. And when you signed up, you probably also got, if you signed up, when you signed up, you probably also got a whole sign up thing that says, welcome to Anchorage ARCVEC. Here's your sign up. Here's your license. Here's your exam information, et cetera, et cetera. Somewhere in there is going to be something that says, if you have any questions, please write.
Okay.
So
yeah, I'm going to try, because my microphone, I think, is just too old.
So. Okay.
I've got a quick question.
Yeah.
Could you put a link in the chat for the that lovely chart with the electromagnetic spectrum?
Actually, I could, I just actually that was part of the information packet that I sent out.
Oh, huh. Okay.
I don't know if I can drag it in, and let me see if I can drag it.
I'll look for it in the packet.
Let me see. Oh, look, I can, and there it is. I just texted it to. I just chatted it to everyone.
Okay, terrific.
So hopefully that works in some kind of format that you can use.
Yeah, thanks.
Okay, other questions? Remember,
I have a question.
No dumb questions. There are no dumb
I've got a
questions.
question.
Yes.
Yes, we have a group in the area that gives the exam periodically.
Yep.
By taking this course and learning and gaining the knowledge and everything, can I test through them?
You can go anywhere you want.
Okay.
I mean, an exam's an exam's an exam.
Okay.
If you're comfortable going in if you're happy going in person and they're happy doing an exam session, then just walk in and do it.
Okay.
I will not be offended at all. My goal, and here I actually wrote down some notes mentally before I started this, and this is one of those things that I was thinking that I should say at some point. Personally, my job is to teach and make sure that you understand the fundamentals behind all this stuff that you're studying. That's why, we're going to go through the book, kinda, but my goal is not to teach you everything that you need just by, looking at the question, right? My goal is the understanding of the stuff behind the book, behind the question pool. When we go through and we do, my kids, they just study the question pool and they're really good at memorizing. Right. My daughter's got her extra class license. She got it when she was 19.
Oh, wow.
Actually, no, she got it when she was 18. Because she's really good at memorizing stuff. When I was 17, I got my extra. And I'll be honest, I had only started engineering school, and the extra class exam, in order to really understand everything on that exam, it helps to be an electrical engineer. It really does. Or to be taught by somebody who is one, because a lot of the extra class stuff is really heavy duty electrical, electromagnetics, antenna design, complex waveforms, stuff like that. It's not simple. It makes perfect sense to me because that's what I studied in college. But for most people, they're never going to fully understand everything that is on the extra class exam, right? My wife also happens to be exceptionally good at memorizing. She did the technician exam just by going through the question pool and studying over and over and over and practicing. She doesn't know.
Hey, Scott.
Yeah.
So I did what you recommended in your first email. Hey, go take these and take a stab at it. That way you can study at what you suck at.
Right.
I took the first one, got 100%. Took the second one, got 100%. Took the third one, got 85%. Took the fourth one, got 72%. I'm like, well, why am I degrading? Am I just that old that I'm defunct? But no, I'm studying for the general alongside the technician. That way, if they offer it, I can just do it.
Everybody will. If you blow the technician out of the water, They'll say, you ready to take, or they'll say, you're ready to take the general?
So that being said, I heard you mention something about cameras. I only have one webcam. How am I able to
You have a phone?
transmit 3 others?
You have a phone?
Yes.
Okay, so basically it'll be a Zoom session and you join twice. Once with the computer and once with the phone.
Okay. I ask, you know, because I'm a geek and a network engineer all at the same time. So I got a lot of crap at my desk, but none of it pertains to radio except for my handhelds.
The hardest thing for you is going to be cleaning off your desk. Some people actually say, you know what, there's no way I'm going to clean off my desk. And they take a computer and they take a phone and they go in the bathroom and close the door.
That's what I'm probably going to do. Is I'm probably going to do it on my laptop and just take my phone and just go sit at my kitchen table, because there's no way in hell that I'm going to be able to show them every angle. I mean, heck, I've got 6 monitors at my desk. You know what I mean?
That's not going to work.
Nope.
But the other thing is that you can't be bothered if you're in the middle of an exam and somebody comes into the room. You have to start it again. So that's why they'll recommend.
My wife will stay at her desk in the bedroom.
Yeah, but that's why some people will recommend, you know, you go in the bathroom and lock the door and put a sign up that says, taking an exam, don't bother me. So
yeah, if I didn't live in an 850 square foot apartment with 1 bathroom, I would do that.
Yeah. All right. Any other
no,
questions?
I'll figure it out.
Other questions? And by the way, if you are up to it, you can take the technician general and extra all at one sitting. I've tested a half dozen people who've done that.
I've thought about it, but I'm still stumbling. I'm about 82% on the extra right now.
Wow, that's actually so my philosophy is if you get 85% or higher 100% of the time, you're ready. So that's what you aim for.
I'm at about 82% right now. So it's if I can take all 3 on Friday, I'm gonna do it. You know what I mean? It's just that simple.
Yep. Cool. All right. Other questions before we go to alternating and direct current? Okie dokie, here we go. No other questions. What we're going to do now is we're going to branch into another area of electrical stuff. Okay, so this is, once again, a battery. A battery has a positive terminal and a negative terminal. And if we draw a resistor right like that, the current will go this way, and the current will always flow in the same direction, represented by the letter I. But now, let us say instead that we took this battery and we redrew it, and we had this battery such that there was a person sitting right next to the battery who every so often would take the battery, disconnect it, and instantaneously flip it so that the plus side and the minus side were reversed. If we were to do this, what would end up happening is that the current would almost instantaneously change direction, because we're now pushing the plus into this side, so the current would flow this way. Well, once we had that going, let's say that the person who is now very busy changing that battery out, and go like this, and all of a sudden now we have to redraw the arrows again. And now that everything's connected, we redraw the arrows. Okay, so now the question is, when this happens, we can say, okay, well, let's draw a graph of what the voltage looks like being generated by the battery. So we have a plus and we have a minus, right? When the battery is connected in the positive direction, we look like this. Then all of a sudden, somebody comes along and they instantaneously switch it and they turn the battery around. And then they wait a period of time and they turn the battery around again. And then they wait a period of time and turn the battery around again. And then they take a period of time and turn the battery around again. Okay. What does this look like?
Sine wave.
It's not a sine wave. It's actually a square wave.
But AC.
But it's AC, because what happens is that your voltage is going from plus to minus to plus to minus. It's very ugly, to plus to minus. And as that happens, what can you say about that? This happens It goes through one full cycle every certain period of time known as T. And if we have a period of time known as T, what does that mean we also have?
Hertz.
We also have a frequency, which is measured in hertz. So what we can do now is we can have this. This is known as a square wave. And what this does is it has a frequency. Okay, so now we're going to redraw our circuit and we're going to introduce because most things well, there are certain things known as square waves. Square waves are particularly ugly. They actually are very, very efficient at delivering power because if we know that from the formula P equals I times E, which actually we can draw in the circle as well. If we have P equals I times E and we have plus and a minus, is that partially up to the top or is that all the way up to the top and then all the way down to the bottom? That's full voltage, which basically means that our power at the top is going to be really high and our power at the bottom is really high. And in fact, we can prove this by going like this and combining two equations, P equals I times E. And what's the other part of Ohm's law, everyone? E equals what? I want everybody to get I times R.
I times R.
I want everyone to get used to doing this. Okay, so now what we can do is we can rewrite this for I is equal to E over R, and we can substitute that in right there. And P is equal to E squared over R. So now if my voltage goes like this, and my E is plus and minus, what is this squared if this is letter E? It's E squared. If this is minus E, what is minus E squared? The minus goes away. The power is always full. Whether or not the voltage is full positive or full negative. So a square wave actually delivers full power all the time. Now, if I were to,
question.
Yes,
With the square wave, is E positive and E negative always the same value?
Yes.
Just
yes,
opposite polarity?
yes. But now what we're going to do is we're going to introduce, instead of a square wave, we're going to introduce a sine wave voltage, which looks like this. So at the peak, this is plus E. And at the negative, at the bottom, this is minus E. But how about all that time in between? How about all that time in between? It's something considerably less. So at the peak, we have P is equal to E squared over R. And at the bottom, we have P is equal to E squared over R. But how about the rest of the time? How about when the voltage E is 0? How much power do we have right there?
None, 0.
None. E squared over R equals 0 over R is 0. So what we have is a power relationship. Darn it. There we go. What we have is a power relationship which peaks at the positive plus, or the positive and the negative, and it looks like this. That's not a very consistent power diagram, is it?
No.
No, it's not. But how about if we had a square wave?
Yes.
It would be, because we're basically either full on or
Or
full
full off.
off. That's right. So our power diagram for the square wave would look something like that. So now the question is, if we take the square wave and just replace that with DC, a square wave power-wise is indistinguishable from DC, because now our voltage is, let's say, up here. that's going to translate to our power down here. That's going to be constant.
So I
now-
do have a quick question, sorry,
Yes.
about the square wave. Is that really even a wave then? If it's just
Oh, yeah.
more like
Oh, yeah.
dotted lines of +1 and -1?
Sure. I mean, you can have a triangle wave.
Yeah. I mean, and the square one is true power because it's on or
Yeah.
off.
And in fact, most digital logic is square waves.
Yep. Because it's on or off. There's
It's
no
either on or off.
variations.
Yep.
Most music is too.
Yeah.
Binary.
Square waves are really noisy. It turns out if you go through a Fourier or Laplace analysis of a square wave, it actually contains a fundamental sine wave plus harmonics, which are multiple frequencies of that frequency.
That's really cool.
Yeah.
So power is always noisy.
Yep. It depends. If you buy so that brings up the question, like, let's say you buy an inverter, if it's a true sine wave inverter versus an inverter. Because it's a lot easier to make square waves from DC than to make sine waves.
Right.
Or when you clean up a square wave, it turns into a saw wave.
Yeah. Ideally, it turns into a sine wave, but that takes a lot of filtering, which we're going to get to also. See, this stuff is so much fun. Okay, so now the question is, if I were to take this sine wave, which now generated this power diagram, and I were to average out this power over a period of time, I would find that it's actually something like that because of all the zeros.
Averages.
This is actually known as RMS, which is root mean square, which is about, if we were to look at the voltage that generated this, we would find that the voltage that generates the same amount of power as a square wave has a peak that is 1.4 times the square, 1.4 times the DC, which is why we're going to draw this one more time. So here's our sine wave. Okay, everyone. Has anyone ever plugged anything into a wall socket? Raise your hand. Okay. What is the voltage of a wall socket? How many volts?
110.
120 volts
20
AC.
volts AC.
Okay. If you were to actually stick an oscilloscope is a device that measures voltage versus time, you would find that it looks like this, right? Doesn't that make sense? I mean, it's AC. It goes up and down like a sine wave. And what you would find is that as you took measurements, you would find that this is plus 170 volts. And this right here is negative 170 volts. Now, this is weird, right? Because what do we call this voltage in the wall? That's called 120 volts. Yeah. This is actually 120 volts RMS.
Yeah, you're reading me.
Which is root mean square. This is if we were to take a DC equivalent voltage that made the same amount of power, it would be 120 volts DC, except that we don't have DC. So in order to make that, we actually would say, okay, well, here's our 120. In order to do that, we actually have to go all the way up to 170 and all the way down to negative 170. So if you were to measure it, you would find that you actually have considerably higher voltages in there. So just an interesting thing when you go to buy a meter, because everybody at some point here is probably going to end up buying an ohm meter or a voltmeter or an ammeter, and you will find an ammeter or a voltmeter that says true RMS reading. True RMS means that it actually does a power calculation on the meter, on the voltage waveform. If it's not true RMS reading, it's basically just looking at the peaks and the valleys and assuming that what's coming in is in fact a sine wave. A true RMS reading voltmeter will actually measure, let's say you have a triangle wave or a square wave, and actually tell you what the power components are in there. how much power is being delivered. So that's just an interesting point of when you go to purchase equipment. Okay, so now what we're going to do is
Hey,
we're going to draw
Scott?
our, yes.
Quick question.
Yep.
When you refer to power there, it sounds like there's a confusion between power as E times R or E times I versus power as voltage.
Right. Well, it's both, because P is equal to E times I times E, and E equals I times
R.
And I can do algebraic substitution and rewrite this. I can write P equals I squared R. I can write P is equal to V squared, or bye, Nate. Have a good trip. E squared divided by R. So those are two alternate ways to write it.
Okay. But those two powers,
they're all the same.
Okay. Okay.
Well, no, because you've got the expressions for them, but power is expressed in watts.
Yep.
And I is current.
Correct. But in a simple circuit, all of those forms are valid.
Right.
Those are all valid ways of representing power. And again, the important thing to note is that if you're looking at RMS, RMS relates to how much power a particular voltage will make. So if I have a battery, let's say, let's go with battery that looks like this. And this is 120 volts DC. Well, if I were to draw that, I would see that the wave looks like this, right? It's always 120 volts. This would also be equal to 120 volts RMS. It's the same thing. But if I were to draw instead this, which is a sine wave, and say this sine wave is 120 volts AC, not RMS, that would mean that my peaks and my valleys would be at 120 and negative 120. And in fact, this would be, if I were to draw this as RMS, because it doesn't make as much power as the DC form, it would make about 70 volts RMS. Because RMS relates to power, the ability of an electrical waveform to make power on average. The key is that it's like an average, it's an average power over time. So because this is confusing, we typically specify, and when I say typically, I mean virtually 100% of the time, this is 120 volts AC. It is implied that it's RMS because nobody does it the other way. Because nobody would write 120 volts sine omega. That would be a smaller waveform, but nobody does that unless you're in engineering school. If we're doing higher voltage and we're using 480 volts, which I sometimes do at work, that's 480 volts RMS, which means that when you actually look at the peaks, it's actually 1.4 times that, which would be about 670 volts peak. You'd have about 670 volts peak. Now, where this actually does become important, and this is the kind of stuff that's on the general exam, where this does become important is if you are, let's say, putting this voltage through a capacitor that looks like this, which we're going to get to very shortly. That capacitor had better be able to handle all those peaks. If the capacitor is rated 600 volts, your capacitor is going to blow up. Because even though it's 480 volts RMS, you have to know that the peak voltage is considerably bigger.
Not to jump ahead, but is that why you would use a fusible link?
We're actually doing fuses right now. Okay, so now we're actually doing literally right now we're doing fuses. And so we're going to have a voltage of 120 volts AC RMS, and we're going to have a resistor that is, let's say, 10 ohms. Okay, so we're going to go through our current calculation. We're going to have two circles. We're going to do E equals IR. That's the first one. We don't know our current, so we have E divided by R, which is 120, divided by 10 is 12 amps. So we know our current of 12 amps. Okay, so now what's the next thing we need to do? We want to figure out what our power is. What's the formula for power again?
P equals I times E.
P equals I times E. Very good. Like that. Okay, and we don't know our power. This becomes times I times E. Look at what's going through the resistor. And interestingly, because you notice we only have two components, the battery or the voltage source is the source. It's providing power, and the resistor is burning it up. They have to be equal. So that's 12 times, well, we'll use the battery. 12 times 120 is 1,440. Now, let's say we didn't know what the battery was. Let's say we had no idea what the battery was. We were just looking at the resistor. Well, we could rewrite the power equation as I squared R. We could also write V squared over R, but that's 12 times 10. And what do we get? 1,440 watts. So we get the same answer. Look at that. How convenient. That's good, right? Because now we don't actually need to know what the battery is. We just need to know, what's going through the resistor. Okay, so now that we've said, okay, we're drawing 1,440 watts, where is that wattage coming out? What is it being turned into?
Power.
Well, what kind of power? Now the power has to be dissipated as what?
Joules.
What's it being dissipated as by the resistor?
Heat.
Heat. Okay, so let us say that we have a 1,440 watt resistor. Where do you find something that big? There's a couple places I can think of. Toaster oven.
Space heater.
Space heater, yeah. Hot water heater. Usually those are a little bigger. Yeah. So we have 1,440 watts. Okay, so now let's say that we were a manufacturer, and us as a manufacturer built a 1,440 watt space heater. And we sold it as a 1,440 watt space heater. So looking at what we just built, there's our 1,440 watts. We just sold it as a 1,440 watt space heater. There's our advertisement. And we have 1,440 watts, right? We just sold it as this. Okay. What current rating would we have to say when we sold it? Would we sell it with? We would have to actually specify the electrical stuff to be hooked up to. So what would you say when you sold this thing? What would you say? What would you write on the package? 120 volts AC.
12 amps.
12 amps. Yep. So that way somebody knows what to hook it to. Okay. So if I were selling this, would I put, let's say, super heavy gauge wire right here or not? I would probably, in order to keep my costs down, put the exact gauge of wire needed to carry that current. Well, if I'm carrying 12 amps continuously, I would probably go with number 14. Whoops. I would deal with number 14 AWG wire. I think that would be prudent. You know, it can handle it all day, and it's not doing anything that the resistor is not capable of doing, and it keeps the cost down, which means I can make my profit, right? Makes perfect sense. 14 gauge is good up to 15 amps. So now, how do I know that? Because the books say so. Laura, that's a good question. 14 gauge is good for 15 amps. This is one of those advantages that that comes about when you build electrical stuff for a living, like I do. 12 AWG is good for 20 amps. 10 AWG is good for 30 amps. So now I could, if I really wanted to, I could decide, well, you know, I'm going to spend a little more money and cut into my profit by replacing that 14 gauge with number 12. Right? But why would I do that when it costs me more money? And no, you won't need to know that for the license. But it is just generally good to know, because this is this is how your house is wired. So let us say that, okay, well, then I'm going to build this exactly as it's built, you know, exactly as this drawing says so. So, but let's say that instead I had a little oops happen, and this new resistor on here, there was a partial short circuit in this resistor one day. And all of a sudden, my resistor was now only 5 ohms. Right? So we're getting into some uncharted territory here. So we're going to go through the power calculations again, right? So I'm going to have to recalculate my current. And I'm going to have to recalculate my power. So what's my current calculation? What's Ohm's law again?
E equals I times R.
E equals I times R. Okay. And so my new R is only 5 ohms. So I is equal to 120 divided by 5, which is 24 amps. What was my old current? It was only 12 amps.
12 amps.
Okay, so if I went with my number 14 AWG wire, which is good for 15 amps, what would happen to that wire?
It burn up.
It would burn up. That's right. Now let's go to the next step. P is equal to I times E. Okay. And if I now have 24 amps and 120 volts, then we have P is equal to 120 times 24 is 2,880 watts. What would happen to my resistor, which when I bought it, it was capable of dissipating 1,440 watts? And all of a sudden, it's going to be dissipating this much energy. What would happen to it?
Overheat.
It would overheat. Okay, so clearly I have a problem here because I'm also connected to my house wiring. And what did I tell my customer the current was? I told the customer my current was 12 amps when you plug it in. And now instead I'm drawing how much? 24
amps.
Okay, so the question is, which of these things is going to burn up first? And the answer is, I don't know. And neither do you. And neither did the builder of your house. So what are the 3 options? The resistor burns up in a little puff of flames and it becomes an open circuit. That's option number 1. Option number 2 is that this wire gets really hot. It's inside it. It overheats. It causes smoke and it burns up. Okay. Option number 3 is that this wire, which is going from your device to your wall, and hopefully is not laid out under a rug, gets really hot and burns your house down. Or the other one is that this wire that's inside the wall gets really hot and catches fire and burns your house down. None of these is a good thing, right? I would say that none of these is a good option. There are some that are worse than others, but none of these is a good thing. So what we do at that point is we have an overcurrent device, which we place at this end of the circuit, which says this is a 15 amp circuit breaker. That would be on your breaker panel in your house. We also take this and we take this circuit that we're building and we put a fuse in there or a circuit breaker that says 12 amps or 15 amps or whatever it happens to be, so that if it senses a current going through that device that is higher than expected for whatever reason, it's going to trip. It's essentially a sacrificial element that you've placed in a circuit, and this is known as a fuse. A fuse is designed to prevent current overload, or which will cause damage to your equipment, damage to your wiring, or burn your house down. Any questions about that? Okay, so why should you never, unless you know what you're doing, replace one fuse? Let's say a 10 amp fuse keeps blowing and you go and replace it with a 20 amp fuse. Why would you never do that?
It'll fail somewhere else.
That's right. It'll fail somewhere else. That'll burn your house down.
Because you're going to cause a wire fire.
Mm-hmm. It'll burn your house down, and nobody wants that. All right. Any questions on protective overcurrent protection? No. Okay. So Ohm's law, overcurrent protection. Okay, now we're on to series circuits and parallel circuits. Okay. Yesterday was Christmas, so this is a very apropos discussion. So we're going to draw a wire. Actually, we're going to draw an AC circuit, and we're going to have a resistor and a resistor. Okay, so this is known as a series connection. Just like if you're sitting on an electron and the electron is moving through the circuit, the electron has to pass through everything. Similarly, if you were watching a TV series, you would watch one episode, then the next, then the next, and the next, etc. Okay. Yes, Christmas tree lights. Okay, so if we were to do this, let us say that this particular system had a resistance of R1 and a resistance of R2. And this is our battery E. We can write our formula. E is equal to IR. Okay, so our electrons, our flow of electrons, our current has to pass through both resistors. It would make sense that our resistance is equal to R1 plus R2. And in fact, that's true. Now, if we were to go through here and see if these were the same, then we would have the same voltage drop across both of these. Well, if these were if the two resistors were the same, then we would have the same power going through both of them, and both of these would be lit up at the same brightness if they happen to be Christmas tree lights. But if these were a little bit different, so that R1 and R2 did not have the same values, the current still has to go through both, but we have different resistances. And then because E is equal to I times R, P is equal to I times E, we would actually have different amounts of power being dissipated in each of these, and power turns into different intensities of light, which means that our Christmas tree lights would be brighter or dimmer from one to the next. The other thing about this is, let's say that we were to wire our house this way. If, let's say, we have something happen, which is not all that uncommon, which is we have that. And we're going to replace that like this. Okay, so this whole thing is called a circuit because we've now opened the circuit. This is called an open circuit. Well, what's the resistance of an open circuit? How many ohms?
Infinite.
That's infinity. Okay, which means we get no current flow. If we have no current flow through resistor 1, how much current flows through resistor 2?
0.
0. This is our Christmas tree lighting scheme, where if we lose one light, it blows out the entire string. So this is why we don't wire our houses this way, because if we were to do this and these were lights or like a microwave oven or something like that, as soon as we pulled out a plug or pulled out a light bulb, all the lights would go out. So this is why we don't do that. So in a series circuit, what's important to remember in a series circuit is that all of the devices experience the same current because the current has to flow through all of them. So we can redraw this circuit in a different way. So we're going to draw it like this. Battery, and here's a resistor, and here's a resistor. And if we were to think of it like this, these resistors are physically drawn in parallel with each other. If I've done a good job with my drawing. R1 and R2. This is our E. So now the question is, what voltage is experienced by R1? It experiences voltage E. What voltage is experienced by R2? That's also E, which means they get the same voltage or the same E or the same V. But that also means that the current that flows through the two of them is proportional to the resistance. So this would be I1 and this would be I2. The total current supplied by the battery or the wall voltage or whatever would be I, and I2, I equals I1 plus I2. Because you can't have, there's no accumulation of electrons in this case. So the total current that's supplied is I1 plus I2. So now here's the tricky thing here. This is the way our house wiring is done. The reason being, what happens if we pull resistor 2 out of the circuit? What happens to resistor
Interrupts the flow.
It interrupts that flow, but does it do anything to the other one?
No, it's isolated.
It does not. That's right. Okay, so now let's say that we're going to add something to this, and we're going to make this R3. These are also known as loads. A load is basically something that uses power. So in this case, we have, let's say we have a microwave. And we have a stove. We have a stove and we have a coffee maker. Okay, the microwave draws a current of 10 amps. The coffee maker draws 8 amps, and the stove, we'll change that. We'll make it a deep fryer for frying your turkey. Electric deep fryer. Why not? And this draws 6 amps. Okay, so this is instead, we're going to replace this with house wiring, which is AC. And this is a 15 amp circuit. And here's our 15 amp circuit breaker right here. So there's our 15 amp circuit breaker, which is somewhere in the bowels of your home, in the circuit panel, probably in the garage or the basement or something like that. Okay, so what happens if we turn on the deep fryer and the coffee maker? How much current are we using?
14.
14 amps. Okay. Well, we have not tripped the breaker. How about if we turn on the microwave?
Pop.
No. How about if we only turn on the microwave?
No.
No, because that's only
It's
10
just
amps.
10 amps.
What if we are running the microwave and somebody turns on the coffee maker. Pulling 8 amps and you trip the circuit breaker.
Right.
Now you say that's annoying, but what it's really done, is it has kept this wire right here from carrying too much current and burning the house down. That is the purpose of again, overcurrent protection. And that's why parallel wiring is a great thing, because parallel wiring allows all the devices to carry, to experience proper voltage. But again, what happens there is that your current adds up, and you can as this happens in my house, it is possible to basically trip a breaker as a result, just like Apollo 13. Exactly. Okay, so we are now on to see what section we're on. We just did parallel, we did power. Okay, we're on to math we're on to conversion factors. Okay, so now in the book, we're on page 15. And it says math for electronics and conversion of electrical units. And if anyone is curious, it looks like this. Math for electronics and conversion of electrical units. All right, everybody see that in the book? Okay, this seems daunting, but it's really not. Okay, so let's say that we have a frequency of 311 million hertz. Okay, so for the most part, we don't really care about all those zeros. Those zeros just take up a lot of room. Fortunately, we have the ability, by using prefixes, to sort of absorb those. Well, we know there are 6 zeros there. And every time, let's say we're going to start with 311 and we're going to multiply that by 10. 3110. We're going to multiply that by 10 again. We're going to multiply that by 10s until we get up to that number. And we will have done that 6 times. By convention, we can write that factor that we've multiplied something by 10 6 times as 10 to the 6th. That's 10 to the 6th power using exponents. What this allows us to do is say, well, we can write this as 311 times 10 to the 6th power, which means that there's an implicit million thrown in there. If we were to multiply all that out, we would get the same exact number as we have up top. Now, we can also take that and we can use our prefixes. We can go with, let's say, minus or 10 to the minus 6th, which is going the other direction. That's dividing by 10s. That's represented by micro. 10 to the minus 3rd is milli. 10 to the 3rd is kilo. 10 to the 6th is mega. 10 to the 9th is giga. 10 to the 12th is tera. And we can also keep going in the smaller direction too. Well, 10 to the 6th is mega. So we could replace that 10 to the 6th, and then we get 311 times 10 to the 6th hertz. Replace that, that is 311 megahertz. So it basically, being able to use individual letters as prefixes for our units allows us to save a lot of room and do shorthand. We could also go smaller. So if we have 0.001 ohm. So 0.001 ohm. Right. So we're going to take this and we're going to start counting backwards. 1, 2, 3 places. So we divided by 10 3 times. That gives us 1 times 10 to the minus 3 ohms. And 10 to the minus 3 is the same as 0.001, which is represented by little letter m. This would be 1 milliohm. So that's useful, but not as useful as some other things. For instance, we haven't gotten to capacitors yet, but we will. Capacitors are usually measured in very, very small things. For instance, 0.00000000022 farads. That's a lot of zeros to maintain, right? Well, we can count those zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 22 times 10. I don't like the yellow. 22 times 10 to the minus 12th farads. Well, 10 to the minus 12th is a letter that we use, little letter p, which is pico. That would be a 22 picofarad capacitor. So this gives us the ability to, again, represent a lot of wasted space in zeros with a single letter, little letter p. So that is why we are able to convert things from one unit to another. It allows us to, save space on a piece of paper, because you look at a schematic, you will see a 22 puff, as we call it, capacitor, and know that it has a lot of zeros in there. Okay. Let's see. Decibels. Okay. So now decibels. Okay. So to understand decibels, what we're going to do is we're going to get into those exponents that we just saw. So for instance, 10 to the 6th, that is represented as 10 times 10 times 10 times 10 times 10 times 10. And it's also equal to 1 million. So there's a couple different ways to write them, right? We could also big letter M, because that would be mega. So now my question is, if we were to take a look at this big number and say something is, okay, so we're on page 19, by the way. We are into something called decibels. And we're going to start by getting rid of the decid, and we're just going to go with the little letter B for bell, named after Alexander Graham Bell, by the way. A bell is a method of comparing one thing to something else, but doing it on a logarithmic scale. So for instance, if I were to say, how many times bigger is 8,000 compared to 2? How many times bigger is 8,000 than 2?
$400.
I hope it's 4,000.
4,000.
4,000 times, right? Okay. How many times bigger is 8 billion?
4 billion.
2? That'd be 4 billion. Okay, these numbers, they're they still make sense, but I could keep adding zeros, and at some point it starts to lose its meaning. So this is like, okay, if we're familiar with the earthquake scheme, that a magnitude 1 earthquake is a lot smaller than a 2, is a lot smaller than a 3, is a lot smaller than a 4, a lot smaller than a 5, and a 6, and a 7, and an 8, and 9 is basically, earth ending, right? Every time you go up by 1 digit, it becomes bigger and bigger and bigger. This is known as a logarithmic scale. And the fact that it's logarithmic means that there's something that's a base that gets multiplied but every time you go up something bigger. A logarithmic scale that's a factor of 10 basically says that this is the exponent. That number that we show is the exponent. So if we have 10, I haven't gotten used to that check yet. If we have 10 to the 0 power, that's 1. 10 to the first power is 10. And then 10 to the 6th power is 1,000,000. If I want to do this in shorthand, I can say that the only real important number here is the exponent. That's how logarithmic scales work as far as earthquakes and stuff like that. So here's the 0, 1, and this is why something that is a 6 is so many times bigger than something that's a 1. And in fact, it's 10 times bigger than something that's a 5 because it came from that scale, 10 to the somethingth power. Well, this has other applications as well for comparing things that are really, really, really different in size and still making sense of them. Again, let's say that we have something that is 4 billion. And we compare it with something that is 1 trillion. Right? That's a lot of times bigger. Well, okay, we can write 4 billion as 4 times 10 to the 9th power, divided by 1 times 10 to the minus 12th power. So now we can take this and say that this is 4, and by our laws of exponents, 10 to the 9th divided by 10 to the minus 12th is 4 times 10 to the 21. Well, okay, so now what we're going to do is we're going to say that this thing called a bell is equal to 10, is equal to the log base 10 of thing 2 divided by thing 1. And they can be anything, thing 2 and thing 1. As opposed to, we're not talking the cat in the hat. I know thing 2 and thing 1. But basically, we're looking at the log base 10 of that. So if we were to look at this, well, you see there's that 10 to the 21st power. Well, the log base 2 of 4 is about 6 or 0.6. But the key here is that you have this 10 to the 21st power. So you could say that this ratio, this insanely big ratio, is it's about let's see, 20.4 bells. So you basically at that point, instead of having this ridiculously huge comparison thing to worry about, you can say that it's that many bells, right? Which then you can convert back if you want to. The other thing you can do with this now, because it turns out that if you have things that are close in number to each other, for instance, we're going to draw something that is 30 divided by something that's 10, for instance. Well, that's only 3 times. That's not that big of a difference. It turns out that that differential is something on the order of 0.4 bells, because it's log base 10 of thing 2 divided by thing 1. So we said, okay, and that's a bell. So the difference here is 0.4 bells. Well, that number gets a little small. So somebody got the idea to take it and multiply that by a factor of 10. So the number of decibels, a decibel is a tenth of a bell, is 10 log base 10 of thing 2 divided by thing 1. And because thing 2 divided by thing 1, this is just a ratio of 2 things. This could be 30 divided by 6. It could be 300 divided by 60. It could be 3 divided by 0.6. All of those would give the same answer because it's the same numbers. right? These are the same ratio compared to each other. So what this allows us to do is to say that this thing is no longer 0.4 bells, it is 4 decibels. Okay, so now where we get useful, where this gets useful is we can take a look at, for instance, a device that takes a small signal and puts out something that's bigger. Anyone know what this is called?
Capacitor.
Nope.
Amplifier.
Transformer or amplifier.
Amplifier. Okay. So the question is, what is the gain of this amplifier? Gain is how many times bigger compared to the input the output is. So if the output, let's say, was 100 and the input was a unit of 1, what would the ratio be?
100.
100, because it's 100 divided by 1.
Right.
Okay, so now we have another way of representing it. We can use decibel. dB is equal to 10 log base 10 of 100 divided by 1. This basically means, to what power does 10 have to be raised to get 100?
2.
That would be 2. 10 times 2 is 20. That would be a gain of 20 dB. Similarly, we could run this in reverse, and we have something called an attenuator. An attenuator takes something big and makes it smaller. There are actually applications for things like that. Make a small copy. This is called an attenuator. Let's say this is 100 units and this is 1 unit. So what would my difference be, my output compared to my input?
0.01.
So if I were to take that and I go log 10 times log base 10 of 0.01, this by convention is 10 to the minus 2 power. So obviously 10 would have to be raised to the minus 2 power. So this whole thing becomes 10 times minus 2 is minus 20 dB. Now, where this really, really becomes useful is, let us say that I have a signal that comes in with 1 unit, and I measure it over here, and this has a power level of 100, and it goes through some feed line that has some loss, and we get 22 units out here, and this goes into an antenna, and this has, we can't really measure this over here, right? We'd actually have to collect all the energy that came out of this antenna in order to do this. This is a really hard thing to do. But what we can do is say that this device has a gain of 20 dB, because 100 times is 20 dB. And this is about minus 5 dB. And this antenna has a gain of 11 dB, because that's how it was built and that's how it was bought. And okay, so how many dB is this? 20 minus 5 plus 11. Somebody add those up. Just add them up.
26 dB.
26 dB. Okay, so in this direction, compared to the 1 watt, our gain would be 26 decibels. Well, every time we go up a factor of 10 dB is 10 times. So 10 dB is 10 times. And now this is where it gets, this is where you really only need to memorize 2 things. 10 dB is 10 times, and 3 dB is 2 times. And we can just add them up. So 26 is 10 plus 10 plus 3 plus 3. So we start with our 1 watt over here, and we multiply it by 10, by 10, by 2, by 2, and we get 10 times 10 times 2 times 2 is 400 times. So for our 1 watt in, we get an equivalent 400 watts out here, over here in that direction. And what we didn't have to do is we didn't have to go through and actually measure everything. We could just use the math to figure it all out. And the nice thing about decibels is because they're based on that same calculation, this system can become as complicated as we want. So we could have an amplifier right here. We could have our initial circuit. Let's say this is a receiver, and this is minus 120 dBm, right? The dBm is compared to a milliwatt. This is a teeny tiny signal coming into this receiver. And it goes through an amplifier, which has a gain of 70 dB. And let's say a filter, which has a loss of minus 10 dB. And through a gain of something that has another gain of 70 dB, and through another filter, which has a loss of minus 5 dB. And then we use that to power an amplifier, which runs a speaker. We could actually figure out how loud the sound coming out of the speaker is going to be based on the signal that's coming in over here, just by knowing what these individual devices are. Incredibly powerful tool for designing and understanding radio systems, among other things. All right. Everybody ready for a 10-minute break?
Yes.
Okay. Does that
definitely
did that stuff make some sense? So when you buy an antenna and it says has compared to a dipole antenna has a gain of 3 dB, 3 dB is twice the effective power output in a particular direction. So those are the only numbers you really ever need to remember. And again, those are 10 times. Oops. Again, these are the only things you really need to remember.
Draw it in green. That was the better color.
Do green?
Yeah, it was a better color.
Okay.
For some reason, I don't know why, it just showed up better.
All right, let's do green.
Yeah, see?
And 2 times is equal to 3 dB. So a doubling of something is 3 decibels. Multiplying by a factor of 10 is 10 decibels. If it goes positive, we call it gain. If it goes negative, we call it loss. Loss is negative, gain is positive. So if we have a gain of negative 10 decibels, that means it's actually a loss. And it's 1/10. So these are really, really helpful. And the only things that you actually like, you can get really, really close unless you're actually trying to do exact calculations. You can get very, very close just using those numbers. 3 decibels is doubling, 10 decibels is 10 times. 10-minute break.
10-minute break.
10-minute break.
All right. How's everybody doing? I'm sure there are some questions. I love questions. No questions?
None yet.
Is my mic still on?
Yep.
I have a question for you.
Oh, good. I love questions.
So when we started talking about decibels, I thought, this is a measure of loudness of sound, because that's how I've heard it before.
Well, it is, and there's a tricky part in there because what do we say decibels measure? A ratio of.
Yeah, ratios of energy, essentially.
Well, it's a ratio of one thing to another, right? A decibel is just a measure, a ratio of one thing to another in a convenient form. So when you hear decibels of sound, what's it compared to? Exactly. Actually, what it's compared to is the threshold of audibility. So something that's 0 decibels can't be heard because that's the baseline. So it's a threshold of audibility.
It must be theoretical because my threshold of audibility has gone up a little bit since I was a youngster.
Yeah, so is mine.
Too many rock concerts.
Yeah, but when you I do a lot of work in sawmills, and you take a decibel meter and you walk around, and I've got to wear earplugs the whole time, and anything over 85 dB continuously will damage your hearing. So, but again, it's 85 dB compared to what?
I looked up. Okay,
Hey, I come out of concert production. I'm not even going to talk to you about hearing loss because half the time I just say, huh? And getting into ham radio is going to be more fun.
Well, good thing there's digital.
I don't know. There's something about the noise that I just love.
Well, noise is good, but other questions or comments or?
Yeah, Scott.
Yeah.
This is Francie here. I'm going to put my picture back up so you can see us. Turn it here.
Yep.
And I was wondering if you had an answer for on the test questions. If you had an answer for if someone has some disabilities, would somebody be able to read the questions?
Yes.
And does that need to be pre-arranged ahead of time, or how do you work that?
Typically, yeah, because it takes more time, and it takes it's more time spent in the room, and somebody has to be willing to do it. Most people are, though. I mean, I've done it.
Yeah. Would you be able to set that up?
I would. Well, let me see if Kent's around. Maybe he can drop in for a minute.
Yeah, this would be for Amanda.
Hold on. Let me see.
She's right here taking class.
I'm calling Kent. I'll see if he can drop in. Kent, Hey, Ken, are you available to drop in on a class for 3 minutes? All right, let me send you the link right now. What a good opportunity to do.
I'll be listening.
Okay, he'll be here in a sec. And the link.
I got a question for you, Scott, about testing.
Yeah.
So the online test that you had set up for this was already full. I live around Eugene. I was curious, when do you guys have in-person testing?
Second, I believe second Friday of the month.
Oh, okay.
And depending on availability, we can schedule.
So you're doing like the 12th of January?
I think it's the 12th.
Pop by.
Yeah. I mean, if you don't want to wait that long, I mean, the other thing is that this is scheduled to be 20. They could open it up, but it's not a me thing to do. It's
I should send them an email and maybe they'll
Let me do it.
let me in.
Yeah, I saw the same thing, Scott. If they do open it up, I'll sign up.
Okay. So let me see, just making sure. Because Kent is the head of the group, so.
Hey, Scott, I meant to ask you that. With me being in Phoenix, am I on that list for that test on Friday, or do I need to find myself a spot?
If you didn't register, then you're not.
Okay, I misunderstood that part then.
Yeah, the exam is separate from the class.
So I need to find me somewhere to do the exam.
Or you can do it locally. You can do it remotely. There are many testing groups that do it remotely. Anchorage group has exams every day, maybe even Sunday. I don't remember for sure. The GLARG group, which is Greater Los Angeles group, they do tests every day online. There are multiple ARRL groups that do them online every day. I mean, there's so many choices. So, but this one is just the one that we set up so that, if you're ready to do it on Friday, it's scheduled for this class as a convenient.
Yeah, I didn't register because I didn't realize I had to.
Yeah, well, that was down at the bottom of the note, so
Yeah, I saw it and I thought about it, and then being a gig economy worker, things got sidetracked.
Okay, Laura. Hey, Laura, are you around?
Yes, it was Francie.
Oh, okay. Are we going over all this stuff for theory, or is this stuff we need for the? Okay.
Yeah, I'm online.
Yeah.
Oh.
So, I mean, have you started taking practice exams?
I've done a little bit, yeah.
Okay, you need to do a lot bit. You need to. I mean, basically, if you're going to be taking an exam, again, unless you have a background in engineering, and you just basically need to touch up and learn some of the rules and regs, there's a lot of specific stuff. Now, what I am teaching is the basis of radio theory and electronic theory, that if you can't remember something, is the foundational stuff that gets you to the point where you actually understand the material. But there's no there's no way to get around having to be good at taking the test. I mean, that's why there are practice exams.
Well, I guess my question also is, how much do you use this after you get your license?
Depends what you
like
do.
when you're using your radio and doing different things.
It depends what you do. What radio are you going to be using? And the question really becomes, what radio can you use? I mean, there's a license, right? Just because let's say you get a driver's license and you use the driver's license to buy a car, and this is your car, right? And it's a very, very slow, small car. And that driver's license also gives you the ability to go and drive a Ferrari, does it not?
Yeah.
Right? Does the state know what you're buying? Does the state know what you're going to drive when you get your license?
No.
No, they don't. An exam is an exam. It covers the basis, it covers the basics that are required to understand the rules of the road and how cars basically work. So the question is, if I go and decide, okay, the sum total, and I hope this is not what you decide to do, the sum total of my ham radio experience is that I'm going to buy a handheld radio. And I'm going to stick it in a drawer in case of emergency. So the question is, does this preclude you with a technician license from buying a radio, which is a base station radio, and hooking up a kilowatt amplifier and hooking up an antenna system that looks like this, with a whole bunch of Yagis that are pointed at the moon, with a gain of Well, let's say that this is a 50-watt radio and this is a kilowatt amplifier, and you have a forward gain of 30 decibels, which now if you're transmitting with 1,000 watts and you have 30 decibels of gain, that is 1,000 times the power, which gives you an effective radiated power of 1 megawatt in the forward direction, aiming at the moon. Is there any difference in the license?
No.
There is not. So in other words, this is exactly why, this is why I use this little drawing here. There is no difference in the license, which is why personally, I don't care if you use it or not, but that's why you have to go through it. If you want to buy a radio and if you want to buy a handheld radio and just stick it in the drawer, that's your prerogative. But that's why other services exist. This is a very, very flexible license that gives you an almost infinite number of possibilities as to what you can do. It also gives you the knowledge of how to go to that next step. Most people, when they buy an FRS radio or they get a GMRS license, don't have the least understanding of how a system actually functions when you start putting components together, and why you would pick a certain radio or put up a certain antenna in a certain location, and why you need a ground plane if you're using a magnet. I mean, this is, again, all the foundational information that describes what you need to know in order to make stuff work well. So it's really up to you. It's up to everybody. Now, personally, this is, I love using this stuff. I love using it for experimentation. I love the thrill of not knowing where my signal's going to go based on what's happening in the upper atmosphere, which is what we're going to get to soon. And Kent, welcome to our meeting. You got any snow today?
Hey there. We got a lot of snow. Hey, it's science, man. This is science. This is good stuff. Yeah, we've got snow, and it's about 4 below zero here in the Kiski. We got winds out of the northeast at 20 to 30, and it's clear, but it's a little brisk out there.
Yeah. That's winter.
Yeah.
So we had a couple of questions. Number one, we have a limit of 20 on the class, and JD's not going to be around for this one, so I guess is it John who's going to be running this one on Friday?
Now the team will be running it. Yeah.
Okay. So it's 20, and there were some questions as to whether or not that could be expanded, because as you see, this is a pretty big group.
It could. I know one slot just opened up today. I think Emily was not going to be. She elected to reschedule, so I know there is one slot available. Let me.
There were also some other general questions about the testing process, about special dispensation for reading the exam to somebody who's
Special
unable.
dispensation for reading the exam. Okay, those are special cases, and so we can do that. We do under Part 97 have to accommodate folks who have a need for that sort of things. And if there are folks that need that, I would encourage you, Scott, to share my information with those specific individuals and have them contact me so we can talk about that. Okay.
Okay.
Yeah, we'll make it happen. Not a problem.
So where should I go to apply for an open spot if all allowed?
Scott, give him the link.
Well,
there's a slot available right now. Let me just check something here, guys.
Yeah. I think he said he went to the link and it was not there or something.
Yeah, the link currently shows it as full.
Try it again. Try to refresh.
Yeah, I just opened it. It says 20 of 20 claims.
Well, let me see if somebody else applied already this morning to fill that one. Oh yeah, we did have somebody.
It was me.
Yeah, Robert, right?
Yep.
Yeah, let me have a conversation. Let's get back to that question. And how many more do you think you might have,
Well,
Scott?
let's ask around.
Matt Snow for one.
And Chris Gilbert for another.
Christopher Hunt for a third.
Eric
Mickey
Allen for fourth.
Rich Friedlander for fifth.
And McKeesa Upton for a sixth.
Okay.
Arlene, seven.
Okay, it sounds like you got a herd. All right. I just sent a message to Drew. I'm sure we can accommodate. We'll just try to get a larger crew of VEs in. But if we don't get a larger crew of VEs in, it'll just mean that the session's going to take a little bit longer to complete.
Okay, perfect. I appreciate you. Thank you.
Yeah, and I'll let Scott know when that's opened up. Okay.
Okay, thank you.
It doesn't take much for me to do it. I need to confer with the rest of the team and make sure they're okay with it because okay.
Thanks, Kent.
Yeah, no problem. I just got to check with one other guy and then we'll make it so.
By
What
way,
are the
Kent-
questions?
Go ahead. Was there another question? Sounds like not. Hey, Kent, when you see Steve Bloom, say hi to him for me, huh?
Yeah, he's my neighbor.
Is he really?
Yeah. I mean, he's just about 1.5 miles that way.
Okay.
He's like northeast of me, about 1.5 miles. And so if you guys aren't familiar with Steve Bloom, he runs the KL7RA contest station here in Nikiski. It's a world-class contesting station. Basically, they plant tower seeds there and water them.
But only during the summer.
Yeah, there's like 13 towers there. It's kind of crazy with stacked monobanders and that sort of thing. So a lot of gain. Just Scott can help you with those gain calculations on those monobanders.
Laura, remember when I said you can go as far as you want with your license?
Yeah.
There you go.
It's cool stuff. Yeah. So I will say, well, first of all, kudos to Scott for doing this. He does these periodically. I know he really enjoys it, and that's very much appreciated. He's a wealth of knowledge. So you'll be well served here. I would encourage all of you who are going to test to make sure you're taking practice exams and don't wait. You know, if you have a few minutes, take a practice exam and see how you're doing. Okay.
And I say 85%, 100% of the time, and you're good.
Yeah.
That's my
I mean, you got to have a 74% to pass. You got to get 26 questions right. So if you can do that consistently, you're not going to have a problem. And the other thing I want you to know is that, look, the volunteer examiners, we're on your team. We're here rooting for you. We want you to pass. So I know it can be very stressful for folks when they take examinations. We get that, but our message to you is that we've all been there. We understand, and we want you to succeed. So we are absolutely rooting for you. Okay, so we do our best to try to get you relaxed for that and ready to go. Okay, so we're on the same team.
And
Okay.
just so everybody knows, I actually took my first VE monitored exam in 1986, which is just shortly after the program existed, and I became a VE in 1987, and I've been doing it continuously since then. Before that, you had to go to the FCC, and it was scary. This is not, and very inconvenient. This is definitely not.
So you should know, if you care, that the Anchorage ARC VEC was actually the very first VEC authorized by the FCC in 1984. And we administered the very first exams on behalf of the FCC in 1984. So we go way back. So we're pretty proud of that. And we We got the authorization. We're also the group that petitioned the FCC in 2014 to authorize the use of remote exams because we had such a difficult time in getting folks in the remote communities of Alaska in to test or teams out to them to test because of the small airplane travel or boat travel or whatever it was. So anyway, that's where all of that stuff started. So when it comes to exam day, we've got a lot of folks to get through here. So we say that the exam starts at what time? Is it 10
I think it's
Pacific?
10 o'clock.
Yeah. So obviously, you know, when we test you folks, unless there are some of you who are physically in the same location, and I don't think you are, actually, it doesn't really matter. You know, we can only get one person. We do one person at a time. So we've got a team of 3 VEs, volunteer examiners, that will administer the examination or examinations to one individual at a time. So we have to get through all of you. We're pretty good at doing it. So we ask that you please maintain a window of opportunity. We'll basically call you when it's time to come on in and join the Zoom session. Because we don't want you sitting around here on hold or sitting in the Zoom session for hours on end. And it shouldn't take hours anyway, but we'll try to have a very large team of VEs in here to cycle you folks through, okay?
Yeah. And although our chatter is really quite interesting, you know, you shouldn't be subjected.
Yeah, it's interesting. All right. Let me turn this up. What are the questions? Any other questions for folks? For me while I'm here?
Yes. Okay, so once we are actually registered, is there anything else we're supposed to fill out and have ready?
Okay, it's a really good question. So a couple of things for the mechanics. One, when you register, there's actually 3 steps you have to complete. One is the very first step, which is you're registering on our examination platform, and that's the link that Scott gives you to start with. After you do that, we ask that you pay for your examination seat, and you have to complete your examination agreement form. All of that information will be provided. Once you complete your examination registration, there's a screen that pops up that will tell you need to go do those 2 things, and there's a link to it. Also, when I process let's see here. Yeah, you should receive an email from the system telling you to go do that as well. So you get the pop-up on your screen, then an email that confirms your registration. And both of those pieces of information give you the link to complete the other 2 steps. And it'll say, you need to complete these other 2 steps to be completely registered. And if you don't complete those 2 steps, you're going to get an email from me saying, hey, glad you registered, but you still need to do these 1 or 2 other things. And that helps bring it all together for us. Sorry, we're a volunteer organization and don't have the ability to create very fancy custom software to keep track of all that stuff. So we got to put pieces and parts together.
And do you also need to have your FCC registration done before you can even do the exam?
Yeah.
You do. You have to have an FRN. You won't be able to register to take
an exam.
Yeah, without your FRN. So if you don't have an FRN, don't fret. It's really not too difficult. And when you try to register, it'll ask you if you currently have an FRN. If you don't, you'll say no, and you'll say, hey, let me take it to the place where you can get your FRN. So it'll help walk you through getting your FRN. But you can also go on your own out there and just get it and have it available. So come exam time, you'll need to make sure you've got a copy of a current photo ID, government issued photo ID, so you can convince the volunteer examiners that you're really you. Okay, I think that makes sense. We need to have 2 cameras. Don't panic. It's just like you're doing right now with 1 Zoom session, and then we're going to have you open the same Zoom session on another device. Typically, most people use their phone. And on that second device, when it asks you about the audio connection, you're gonna say no, or you're gonna cancel it. Because if you say yes, or if you allow it, or if you think you're gonna be smarter than the system, you can say, well, I'm gonna mute the microphone and turn the audio down. We could do all of that, but it's gonna be painful for a lot of us until you get that done. So the best thing to do is on that second device, just say no to the audio question. And that takes care of that. Once that's done, you probably have seen the example sort of image. We want that set. We'll end up getting that second camera set up so it sort of looks over your shoulder. And we want to see the computer screen that you're taking the examination on, along with your keyboard and mouse and basically your hands. Okay. And then don't worry, the volunteer examiner team is really good at walking you through all of this stuff, but think about placing, getting your room set up now for that exam.
We talked about the bathroom.
Yeah, a lot of people use bathrooms. Just pretend, just think in your own mind that you're the volunteer examiner and what you would and would not like to see your examinee have on their desk or in front of them, example resources that could help you on the examination. We don't want that sort of thing. No posters or things with frequency charts or formulas or all of that kind of stuff. Try to get your desk clear of all materials. Some people find it more convenient to just like put up a sheet and cover things, that sort of thing. If you're running two monitors, we'll have you either turn off the second monitor or cover the second monitor on your computer.
Right. If this
Those
is
sorts
laying
of
out on
things.
your desk, we're probably going to say something.
Yeah, not so much. Anyway, you can use a calculator during your exam, a simple mathematical calculator. If you're using one that's programmable, we're going to ask that you show it on the screen and show us clearing the memories. We will allow you
smartwatches, no smartphones,
no smartwatches, earbuds, that sort of thing. On the calculator, you can use your on-screen, your computer-based calculator, but we'll need to see that. And you're going to be sharing your screen with us, so we'll see all of that. Okay. I think most people, I will go out on a limb here and say that most people typically don't need a calculator to do this examination. If you feel like you need it, that's perfectly fine, and more power to you. You'll be allowed to have a sheet of scratch paper, one blank sheet of scratch paper, which is usually plenty for folks for this thing. And we'll have you show it to us front and back so that it's all good. If you need it. Many people don't. But let's see, we're going to be doing this on the 29th. Is that Friday? Is that right? Friday? Yeah. So what'll happen is once everybody's done, we'll be submitting the applications to the FCC. We submit very promptly. So once everybody's done, we'll prepare the electronic batch file that we submit to the FCC. And within about a top of the next hour, they should have responded already, processing the file. That's hopefully, if the FCC is firing on all cylinders, that's the normal way things go. And when we receive the response to our batch file, at the very same time, you are going to be sent an email. You'll receive an email from the FCC saying, hey, we got your application. Now you need to go pay us. And it'll give you instructions on how to go to their pay site to pay them their $35. When you do pay, please don't try to pay using your phone or a notebook or whatever. Use a regular computer. The FCC site doesn't play well with other types of devices. Just use a regular computer. Make your payment to the FCC. And then typically within about 24 hours, your license will be issued. Now, this is a Friday, so in this case, it will likely not be issued till the following. Actually, Monday is New Year's, right?
Yeah.
Yes.
Yeah, so it probably won't issue out until the 2nd. That would be my guess. Okay. Now, sometimes for various reasons, some applications get caught up in the FCC system and they'll put you into a what's called level 2 processing situation where it requires some manual look-see by a human being at the FCC. I don't anticipate that that's going to be an issue here, but it's always a possibility. And nobody needs to answer this question. It's none of our business. We don't really care. If be sure to answer the basic qualification question truthfully, which some people refer to that as the felony question. Having a felony doesn't preclude you from having an amateur radio license, but the FCC wants to know about it. And there are some special actions you have to do. So if you do answer yes to that basic qualification question, be sure to do the follow-up that the FCC requires you to. And we can give you some guidance in that regard if it comes to that. Okay. Any other questions for me?
How about for retests or later tests if we're not ready to test on Friday?
Sure. Scott has probably shared with you, and I think we did share with you, if you've registered with us and you received a receipt, I believe there's a link in there to complete the rescheduling process. So we'll have you fill out another form and have you register for another session. There's no fee for that. We don't give refunds for exams, but we're happy to reschedule. Okay. If you need that rescheduling link, we can get it to you, or just let Scott know, and we'll have you reschedule. I just had somebody do that earlier today. Hence it opened up a slot. Did I miss, was there a second part to that question? No? Okay.
Oh, no, the one answer, I answered both questions.
Okay, great. Anybody else? Questions?
Yes, I have one. So this one is in continuation of my last speaker. Hello. Yes. So this one is in continuation with the question, the query that my last speaker asked. Say if someone wants to take so there are 3 types of licensing, and if someone wants to take general and extra due to financial constraints, is there a way to schedule them all together?
Sure. Yeah, if you don't want to test right now, we can just you can reschedule for a later date.
Yeah, you can take all 3 at once.
Yeah, you take all 3 exams at once.
You have to pass them all, but you know.
Yeah, I mean the $10 fee. Okay, so let's talk about that. Sometimes people get a little confused. So when you pay us the $10, that's our examination seat fee. It's not an exam.
It's not 15 anymore.
No, it's $10.
It went down.
Okay, I thought it was 15. Okay.
No, it's $10. And that it gives you your examination seat. So if you're able to sit down and pass all 3 exams, then that's wonderful. However, caveat there, please don't ask to attempt an examination that you're not ready for. If you've not practiced it, if you're not prepared to pass that examination, please, I would just say it this way: don't waste your time and don't waste the volunteer examiner's time on this. There are plenty of other folks that are ready to test. You can practice the exam on your own time. There are plenty of sites out there, as you well know. You could take practice exams at your, back in the day before we had online stuff, we would certainly offer people to try if you pass your technician exam. We'd say, hey, give it a try in your general exam to get a look at the exam. The reality is we don't really have that situation anymore. You can look at all of the exams at any time. Now, where I wanted to go with this is that it's $10 for your examination with us. And then you're going to pay your $35 to the FCC. Now, so that gives you a license that's good for 10 years. If during that 10 years you upgrade to general and or extra. There's no fee from the FCC for upgrades. Okay. So you don't have to pay them another $35 every time we submit to them for whether it's an upgrade or anything else. The only time you pay the FCC, there are three times. One, new licenses. Two is renewal of licenses. And three is if you want to get a vanity call sign. Okay, that's it. So no fees for upgrades from the FCC. There is a fee for us to sit to take the exam, but that's the $10. Okay. Hopefully that helped a little bit.
Hey,
Thanks.
Kent, I had a follow-up question for you on that. You said don't waste time if you're not ready for the test. So just on that, I mean, I'm taking this class, I'm reading the book. I haven't really started doing the practice test yet, but I'm going to. Is that going to be enough?
You'll be fine.
Yeah, it should be.
All right.
Yeah, take your practice exams.
Yeah, because right now I can tell you I'm not ready, but I'm hoping that by the end of the week I will be.
You'll feel
hang-
yourself getting better if
Yeah.
you're serious about it.
Yeah. So hang on a second. So Eric, is that Eric?
Chris.
This is Chris.
It's Chris. So I'm looking around. So Chris, I know you say you're not ready, but you also said to me you haven't taken any practice exams.
Right.
You don't know that you're not ready. Okay. All right.
Well, okay, to be fair, I opened up the practice exam application that you guys recommended, and I ran through like the first test. There were a bunch of questions I had no idea yet.
Okay. Fair enough. So if you get,
we've only done 2.5 hours of 12 hours.
Yeah, a lot of stuff's going to come to light here.
Okay.
And yeah, so I encourage all of you right now, today, if you haven't done it already, take a practice exam, get your baseline so you know where you're at. Because as Scott goes through this material and you take additional exams, I think I'm just stating the obvious here. You're going to see yourself improve on these exams. Now, most people take between 12 and 20 to 25 minutes to take an exam. It's all depends on you, but just take those practice exams.
All right.
And if you're not ready, then let's reschedule you. Let's not test you. Let's move you out and we'll test you at a later date. Okay. It's not a problem.
No, appreciate the answer. Thank you.
Yeah. Oh, also, you know what? There was a question. If you're close, so if you tell me, Kent, I'm taking practice exams and I'm usually passing them, I'm getting passing scores. I'm usually scoring between 80 and 85%. And you take your exam and, there's a chance you're going to get a bunch of questions that you didn't see on the practice exams, or it's material you just don't happen to be familiar with. If you tell me, Kent, I'm normally passing these exams, I missed it by 1 or 2 or maybe 3 questions, we're going to give you another shot at the exam right there. Okay, we'll give you another test. Okay.
All right.
Does that make sense?
It does. Thank you.
Because we want you to pass.
Perfect.
Anybody else?
Yeah, Kent. I have a question about how the exam is presented on the screen. Is it like the practice exams, like multiple choice, or is it an audio question? They ask you the question.
No, it's all presented on screen. Basically, when you get to the examination platform, effectively, the examination is one long web page. You can actually scroll up and down through the questions. So while we're here, we're talking about it. We'll address this.
Okay.
It's going to be you're going to read the question. The 4 answers A, B, C, and D are there, and you can answer the question one of 2 ways. You can either use your mouse or your glide pad or whatever and click on the right answer or the answer that you select. And if you do that, you'll typically have to scroll down to the next question.
Okay.
Hold for a second. Conversely, you can also answer the question by typing on your keyboard the letters A, B, C, or D. If you answer a question that way, it'll automatically jump you to the next question. One other item, and I'll let you go. you might happen upon a question on the exam that has a figure or a schematic or an image, and it may look a little bit small to you. If you simply click on that image, it will enlarge so you can see it better. Then click on it again, it'll shrink back down so you can answer your question. Okay?
Okay. I have a little bit limited vision, and usually I have a 42-inch monitor above my computer screen. Will that be acceptable if I show both screens with my second camera?
Yeah, that'll be fine.
Cool, I'm good.
While you're taking the exam, one of the things, and we're gonna go over this at exam time, but when you're taking the exam, a couple things to remember. One, you need to be by yourself. There can't be anybody coming into the room. We don't want you having conversations with anybody, all of that sort of stuff, okay? So you're isolated. Tell everybody, hey, I'm taking the exam, stay out.
It's just me and my dog, and she doesn't show any interest, so.
Oh, very, very good. Well, I'm talking to the whole group here,
Okay.
and we're okay with the dogs. And two, we ask that you please stay focused, keep your head focused on the examination. Keep looking at the computer screen, if you will, within reason. We don't want you looking around the room and all of that I think for obvious reasons, right?
Yep.
So we ask for that. So we try to keep it within those parameters. If something happens, we'll just stop the exam. And because, every now and then something does happen.
Yeah.
And we'll have to stop the exam. And if that happens, it's okay. We'll just start a new exam. That always sucks if somebody's on question 34 and they have to start again, but that is what it is. By the way, the other thing is that when you're taking the exam, you can change the answers to questions. Okay, no problem. You can scroll back and review and change answers to your heart's content. There's no time limit on this. You can skip questions. They're ultimately going to have to be answered, but you can skip questions during the exam. And if you do skip a question, it's going to present as a circle, a colored circle on the top of your screen. That'll remind you that you skipped a question. You could click on that question, it'll take you right back to it. If you happen to get to the last question on the exam, question 35, and there are questions yet to be answered, it's going to jump you right to the first skip question anyway.
Okay.
Okay. All right. Anything else?
Oh, hello. This is Art here. I have a question.
Hi, Art.
This is kind of my first exposure to the ham radio, training that was given by Scott. Thank you, Scott. And I'm honestly, I'm a little bit worried. So I'll try to, once we receive the recording, so I'll go over it and try to glean as much as I can. But besides that, would it be kind of a good idea, like go buy a ham radio for dummies book?
No. Well,
or no?
maybe.
Okay, I don't
But
know.
you won't need it. I mean,
Oh, okay.
just practice, go and, get through the exam, study and study and study, and to the point where you get through the exam, and then go find a club.
Yeah, just so to get so the remember the questions on this examination they're coming out of a question pool. It's a finite set of questions. They are what they are. I mean, theoretically, you could study for this exam by reviewing each of these questions and remembering the right answer for each one. That is an approach that many people take. And some people will argue against that. I think that's a perfectly fine way to do it, because the reality is that even if you do it that way, learning has happened. Okay. Learning has definitely happened.
Yeah.
And the other thing to please remember, your objective is to pass this exam. Why do you want to pass this exam?
So you can start learning.
So you could start learning. That's right. So you could become a member of the club, and I don't mean a radio club, but a member of the club of people that have licenses. And that's when the real learning starts. Scott's been a ham for many years. I've been a ham for 30 plus years. I can assure you that I continue to learn every day. This is the nature of this. This is a learning learning adventure you're about to embark on. And it's cool and it's science. And when you're looking at Hubble or the James Webb Telescope and whatnot, I was just watching a presentation on that right now, and stuff that I learned from amateur radio was completely germane to the explanations I was receiving from these programs, and it helped me understand a lot of this stuff better. So this is a wonderful, wonderful adventure you're embarking on.
Nice, super. And I have another question. And please forgive me.
This is gonna be the last. This is gonna be the last one because we have circuits to do.
Okay, good. So once everybody gets, let's say we get the license and we're good to go, what's the cost? Having, getting a ham radio? Is it expensive?
Start talking. Start visiting your local club.
Yeah, the answer to that.
Have.
Yeah, and the answer to that question is it depends.
I like that.
It can be very inexpensive. It can be very expensive. It's just, so what it's all over the map.
Okay, I see. Okay. Thank you.
So
anything else?
I'm gonna
Scott's cutting me off.
I'm gonna show you guys a picture. I was there. Okay. Does everybody see that photo?
Yes.
See that antenna stack? I got to operate from that station in Finland. That was the group. By the way, Kent, this past fall, I was part of the group that went to Vanuatu and set the CQ Worldwide single sideband record for Vanuatu. And then I went to Finland where I was working. I found the OH5Z guys. They invited me to operate, and I participated in setting the Finnish national record for the CW contest.
Oh, very nice.
But that's their stack. That's, that's $100,000 in antennas. And inside the shack is another $150,000 in equipment. You could spend $200, you could spend $50.
You could, yeah. It all depends on what you want to do.
It helps to become if you don't want to spend a lot of money, it helps to become a good operator and befriend people who have a lot of money who enjoy it. Who are willing to put together a contest station and share it with their friends.
Scott, I'll ping you once I confirm we're going to open up some more slots. Okay.
Yep.
All right. Thank you, everybody. Appreciate
Thanks,
you
Ken.
doing this. And good luck. And remember, we're rooting for you. Okay.
Sorry, I didn't realize I was unmuted.
And if you want to drop in any other time, Kent, let me know.
Okay. All right, you guys. Thank you. Congratulations. We'll see you at the other end.
Thanks, Kent.
Thanks.
Okay. Here we go. We're on
Thanks,
to more
Scott.
circuits. Thanks, Kent.
Hey,
Okay,
Scott, here's a quick example to show Art of how easy it is to get started with your first radio. This is a $25 radio.
Which one are we talking? Oh, yep.
The UV5R.
Yep.
It's a great little radio to get started.
I love and hate them.
We all do.
Yeah.
Every one of us.
Well, thank you. 25. Okay, that's very inexpensive.
Oh man, I just love Baofengs. I don't know why you'd hate them.
because their front end filtering sucks.
Well,
That's why.
yeah. Okay.
Then you can go with something like this,
right?
Which is a much better radio. It costs 3 times as much, but
yes. But the thing, right, and I mean, it's at some point, they say that 90% of the performance is in the first 10% of the price, but there's a certain point when you're even below that, because the problem with the Baofeng is that literally the front end is a piece of garbage. And when I say the front end, we're going to get to filtering. When we get to filtering, you'll understand what I'm talking about.
Okay.
Let me know when we get to filtering. I'll hold it up again so they can understand.
Yep. Okay. All right, here we go. We're going to start doing componentry that is used in filtering right now. And we're still aiming for 1 o'clock being done today because I've got a car to pick up. So, okay. So we did resistors. This is a resistor. Resistors are very often made of carbon. And resistors can also be made of other materials. There's tantalum. There's a few other things. Most often it's carbon. A resistor has a characteristic called resistance. Resistance does not care if it's AC or DC going through it. They just resist the flow of electrons. If I do this, this becomes a variable resistor or a potentiometer. It basically is supposed to indicate that you can do this or this with it and change the value by shorting out a certain length of it. It can also be drawn like that, which is a potentiometer. Okay, there's another device now, which we're going to get into. Resistors, again, don't seem to care whether or not it's AC or DC. We're going to draw this. Okay, anybody know what that is? Somebody take a guess what that is. Looks like a piece of wire, right? It looks like a piece of wire, right? Okay, so now I'm going to make this two-dimensional. So what is that?
A plane.
That's a plane. Okay. So I can make this out of metal. If I make this out of metal, that becomes a metal plate. Okay. So now what I'm going to do with this is I'm going to take this battery and do this with it. What comes out of the positive terminal of the battery and what comes out of the negative terminal of the battery?
Electrons?
Yeah, exactly. So I have electrons coming out of the minus side and pluses coming out of this side. Pluses basically are a lack of electrons. So if there are electrons in this metal, what will happen is if there's no way for current to flow, the electrons will kind of go this way. The electrons will sort of flow up this way, and you'll be left with a positive charge on that plate. Now, this is, how much current is there? Well, there's nothing. Once they're equal, there's nowhere for any electrons to go. So now the question becomes, what if I do another plate down below? And I draw it like this, and I change the color. Let's make it the orangey plate. All right, so now I have an orange plate down below. And I take this orange plate and I hook this up to here. What will happen to those two plates? Well, I will get
Conduct.
Yeah, well, no. Well, you'd think, but no, because they're separated by something. They're separated by a gap. So I would end up with minuses down here and pluses up top because the battery says so. So now if I have a plus up here and a minus down here, what do pluses and minuses want to do?
Right.
They want to attract. They actually generate a force in between the two, which is a physical force which tries to pull them together. And what am I doing? I am physically separating them by some kind of material in the middle, which is an insulator. That could be air, that could be plastic, that could be glass, that could be mica. It could be any number of different things. So basically, I've filled this gap so that electrons can't make the jump and those plates can't smash together. This is known as a capacitor. It basically is a storage unit or a storage device for electrons. So once I charge it up, it becomes charged. And how about if I do this and get rid of the battery altogether, get rid of the wires, and it's already charged up, what happens?
Discharge.
Where?
Oh, it doesn't have any place to go. So it
Doesn't
just
have any
stays.
place to go, so it stays charged. Yeah. So this is how a capacitor stores energy, and because it wants to, the electrons and the positives want to pull those two plates together. This is actually storing energy between a plus and a minus. These create an electric field. This stores energy in an electric field. The electric field is attempting to pull those two plates together, and we are fighting against it by putting something in between in the sandwich. Now, if, for instance, this capacitor and the stuff I use in between has a rating of, let's say, 100 volts, and I charge this up so that this top plate is at 300 volts and the bottom plate is at 0 volts, what will happen? Those electrons that are at the bottom, what will they do? They will puncture the dielectric and jump, basically destroying the capacitor. Because the material inside doesn't have the ability to resist them. So this is a capacitor. So now what I'm going to do is take this capacitor and I'm going to draw another something with it. And this is the schematic representation for a capacitor. Just two parallel plates. Now I'm going to take this capacitor and hook it up to a battery. Plus, minus. Okay. The top plate goes to the plus. The bottom plate goes minus. So now the question that I have is, what happens once it's full? How much current will flow once it's completely filled up? If it's DC, can any current pass through that gap?
It should be a closed circuit. It should be closed circuit. It should be full.
Well, no, it becomes an open circuit. It fills up and you have no additional current. In other words, once these plates charge up, how much movement is there in electrons?
More.
There's no more. No movement of electrons means that there's no current. No current is the same as a circuit that looks like this. That's an open circuit. So what happens is when you hook up this battery in this circuit, and again, this is DC, it's always going the same direction. Once you do that, the capacitor will charge up to the voltage and then just stop. It'll just sit there. So if I were to measure the current, it would be very, very big and then go to zero over time. That's what the current graph would look like. Well, if I have, by Ohm's law, E equals IR, if I have a very big current, the only way to get that is with zero resistance. If I have a very low current, that's infinite impedance or infinite resistance. Well, so this goes from being what looks like a short circuit to an open circuit over time. If I'm measuring a circuit and I see this happen, that means that there's a capacitor that's getting charged up. But now I'm going to make this capacitor a little more interesting because capacitors are really quite interesting. So here's our capacitor. And I'm going to do this with it. Here's our battery. And plus and minus, plus minus. The capacitor charges up. But now I've hired somebody to come over here and take this battery and reverse the battery so that the plus is here and the minus is here. What's going to happen to the pluses that are on the capacitor? And then what's going to happen to the minuses? They're going to flow back until the capacitor is completely empty. And then once it's completely empty, you're going to have the battery refilling the capacitor with pluses and minuses up here.
Right.
Right. So basically the capacitor becomes charged the same way as the battery. But then my employee who I hired to switch the battery out periodically and change the direction is going to say, oh, well, that's done. I'm going to switch the battery again because that's what I was told to do. And now you're going to have backflow of these guys and backflow of these guys. Eventually, those are going to disappear. You'll have no more current flow that way, and the current flow will instead go this way. And you end up with pluses over here and minuses over here. Well, now this becomes really interesting because this guy that I hired to switch this battery has a name. And his name is alternating current. So when I hook up a capacitor to alternating current, if I had no idea what was back behind this wall, think of the Wizard of Oz. I should really make the curtain green. Pay no attention to the man behind the curtain. See if I can see. Here's the green curtain. If I had no idea what was there, but every time that I switched from plus to minus, or then from minus to plus, I knew that there was current flow back and forth and back and forth. What is a circuit called when no matter what happens, the current flows? That has a name. What's that called?
Circuit.
It's called a short circuit. So what that means is a capacitor, when it's exposed to AC in the extreme, acts like a short circuit. Now remember, when a capacitor was hooked up to a DC circuit, it did this. It looked like an open circuit. So depending on the frequency of stuff that you pump into it, capacitors either behave like an open circuit or a short circuit. Now we're going to introduce something else. A capacitor, again, is measured in farads, named after Michael Faraday. So capacitor is measured in farads. The big letter is C for capacitance. The unit is F for farads. And again, for AC, it's a short circuit. And for DC, it's an open circuit. So now what we're going to do, yeah, go ahead. Okay, now we're going to introduce something else. We're going to introduce a piece of wire. And now we're going to take that wire and we're going to coil it. Is that wire any different than a piece of wire? What do you think? Is that any different other than being coily?
Nope.
Nope. It's still a piece of wire. So a wire, if it's a really good conductor, has what kind of resistance? If it's a good conductor, very low. Okay, so now what I've done by doing this is, if you hold up your hand and wiggle your thumb, hold up your right hand and wiggle your thumb, and then you take your fingers and you roll them forward. You're up, you hold your hand, you roll your fingers forward. If I have a current that's flowing this way, I will have a magnetic field that is rotating around the wire. Moving electrons generate a magnetic field. Now, what that means is that if I coil it up, I end up with a magnetic field that in the coil kind of looks like this. It makes loops. This might, if you've ever seen a picture of the Earth's magnetic field and what it does to the for the aurora, this is very similar to that.
You talking about Skip?
No, not yet. Okay, so what we have here is we have a coil of wire that now doesn't really know the difference for DC. So if I hook up DC to it, I'll get a plus and a minus. The current goes this way. And as it's doing that, it will make a magnetic field that loops around and just keeps looping around. And this is what we call an electromagnet. If anyone's ever taken a nail and wrapped a piece of wire around it and hooked it up to a battery and used it to pick up paper clips, this is exactly what that is. It generates a magnetic field in the core of the coil. There's nothing there to limit the current. So for a DC circuit, an inductor looks like this, which is a short circuit. This is a capacitor, and this is an inductor. DC, short. Okay, but now, once we have that magnetic field formed, that's energy, isn't it? Well, okay, so if I have magnetic field energy making a circle around this, and I suddenly decide that I want to switch the direction of the electricity that's making it, what is already in there? We have this magnetic field energy, and it's floating around in space around it. what will happen is that this energy has to go somewhere. Where it goes is that it actually generates a reverse current fighting back against the thing that is trying to make a new current going the other way. So what ends up happening in the case of AC is that an inductor does not like to be pushed that way. So in an inductor, you have AC, and in the extreme, an AC, and it looks like this. And notice, now that we draw the line, these things are completely opposite, aren't they? The capacitor for AC looks like a short. An inductor for AC looks like an open. A capacitor for DC is an open circuit. An inductor for DC is a short circuit. So what we can do with this is a really cool trick. We can do, for instance, a power supply right here, or some source of voltage, which is AC and DC. We don't even know what they are. We don't care what they are. What if we do this? And we have AC and DC. Which way will the AC go and which way will the DC go? The AC will flow through the capacitor.
Don't they go in opposite directions?
The AC will go through the capacitor and the DC will go through the inductor. These two things, called a capacitor and an inductor is a letter L. Its units are henries with the letter H. What will end up happening is that this device will separate AC and DC. This would actually be called a low pass filter. We've basically taken the AC and we've shunted it back to the power supply, and all we're left with is the DC on this side. DC is zero frequency, right? So there you go. This is a filter that uses capacitors and inductors to separate out AC and DC. And I see Kent is back. Or he was back. Oh, I guess he's going to come back in a minute. Okay, so now what we're going to do is we're going to introduce one more thing about this. Okay, so we have AC and DC. AC looks like this. DC looks like that. DC makes current that goes one way. AC makes current that goes back and forth in time. These are fundamentally different things, but aren't they just both movement of electrons? Right? I mean, they're just movement of electrons, right? What it comes down to is what effect moving electrons have and moving them from place to place. So again, an inductor is not very happy with AC. An inductor is just fine with DC. A capacitor is fine with AC, but not so good with DC. And it's because of the change of direction of things. So now what we're going to say is, okay, so we've kind of established that there's this in the extreme, right? Okay, but what happens do all capacitors and inductors behave the same? If we have this capacitor and we have this capacitor, which is much, much bigger, which one is going to have more capacitance, would you say? The bigger one or the smaller one? This one with
The bigger one.
The bigger one is going to be much, much bigger because it has a lot more room to store electrons. If I have an inductor that's this size versus one that's this size, which one is going to have more inductance?
The larger.
The physically larger one, right? So what happens at that point is that obviously they're going to behave differently. One is going to make bigger magnetic fields, and one of them is going to make bigger electric fields. They're going to behave differently at different frequencies. So we have this letter F, which is frequency. And now we're going to introduce another concept. What was that resistance thing? What is resistance measured in, everyone?
Ohms.
Ohms.
Okay. So we have resistance that's measured in ohms. Okay. Does a resistor care whether or not something is AC or DC?
No.
It has
Nope.
no difference. That's right. Okay. But now if I were to take an inductor and a capacitor, do they care if it's AC or DC? Do they behave differently? And the answer is yes.
Oh yeah.
Very, very differently. So the question is, how differently do they behave? So what we're going to say here is we have to add another factor to this. And
I was
in
going to say, you
fact,
could have a shockingly good time.
you could, yes. I actually learned how to do arc welding once like that with a capacitor that was fully charged. So what we're going to do is we're going to introduce one more thing. So we had actually two more. We had resistance. Now we also have something called reactance. And we also have Z, which is impedance. Okay, so this is resistance. X is reactance and Z is impedance. And reactance is literally how a capacitor or an inductor react to certain frequencies or certain voltages that come into it. Well, as it turns out, these are perpendicular amounts. So this is our resistance and this is our reactance. And notice that they are on perpendicular axes. So if it turns out we have resistance here and reactance here, our total impedance is this right here. Does everybody remember the Pythagorean theorem?
No.
Z squared equals X squared plus
Yep.
R squared, or X squared plus Y squared equals Z squared if you have a right triangle. So what happens here is that resistance is resistance and reactance is kind of how something behaves in response to AC current. Well, as it turns out, a capacitor behaves in this formula, 1/2 pi FC. An inductor is 2 pi FL. Okay, so we have one of them for a capacitor and the inverse for an inductor. And actually what it turns out is that a capacitor goes this way and an inductor goes this way. Inductors will go positive, capacitors will go negative. And the interesting thing about this is that since they go plus and minus, could you set them so that they are equal and cancel each other out? What do you think?
Definitely.
Definitely. Okay.
100%.
So here we go. We're going to draw this. We're going to draw a circuit that has one of these and one of these and one of those. The thing on the left is a resistor. The next one is a capacitor measured in farads. The one on the right is an inductor measured in henries. Okay, so we're going to have resistance, and the impedance of a resistor is equal to just the resistance. The impedance of a capacitor is negative 1 over 2 pi FC. And for the inductor, it's 2 pi FL. And we actually have to introduce this little I, letter I, meaning that it goes up and down instead of side to side. Notice that these now have opposite signs. This one is a negative, and this one is a positive. The sum of all of these is the impedance for the whole circuit. So it's R minus I over 2 pi FC plus I 2 pi FL. We could take those, and our circuit impedance will be minimal when those two things cancel each other out. So if we were to take these two devices, a capacitor and an inductor, and we could make them variable like this and tune their values by changing them physically so that the C and the L at a given frequency would cancel each other out, we would end up with frequency is equal to 1 over 2 pi square root of FC or LC. This is not on your test, but this is super important. This is known as resonance. And the reason that it's important is because if our resistance is very low, this means that our circuit impedance will be very, very low. And if we were to draw an impedance versus frequency graph, we would get this. And if we get that, what does that mean right here at the dip? It means that our ability to stop AC current is practically nothing. If we are trying to, let's say, filter out a bunch of frequencies that look like this, which one is going to get through? The answer is only the one that we want. This is the basis of radio. This is the basis for tuned circuits. This is why if you find a 60-year-old radio or something and you take the cover off and you see this big capacitor that's tunable, which might look like, I'll show you a picture. And people have maybe seen these. Here we go. Let me just share this. Has anyone ever seen one of these?
Oh,
This is a variable capacitor. This is a capacitor that you can change the capacitance on by moving the plates around. By having variable devices, what you can do is you can actually tune a radio. You can tune a circuit. You can tune a filter. You can build something that responds to one frequency but no others, which is an incredibly powerful thing, because if we're listening to, let's say, the universe, and the universe has radio frequency energy that goes from 0 hertz up to infinity hertz, how are we going to ever listen to just one frequency, independent of what that frequency is? How in the world do you pick out just one? And the answer is you have to build something that blocks out almost everything and just opens up a window right where you want it to. This is the essence of a thing called filtering. Baofeng, piece of crap. The filtering is awful. which basically means that if you're in an environment that has a lot of RF floating around, which is radio frequency, the receiver gets completely swamped. That is exactly why that radio doesn't work well in high RF environments. If there's not a lot of RF floating around, it will be okay. As soon as you hook it up to a bigger antenna, or you, let's say, go into a city where there are pagers and other things, essentially the receiver can't see anything because the filtering is terrible. It's like walking into a room where you have 10,000 watts of light and trying to see somebody who's holding a flashlight. Your eyes don't have that ability to filter anything out at that point. So Matt, does that explain that? Okay, good. Okay, so let's get back to basic circuits. Okay, so what we're talking about now is basic circuit design. And I'm sorry for that little jog to one side, but I think it's actually kind of important. So, okay, so now we're into circuit design, and what I'm going to do is just basically pull up the book, because they do a better job of this than I could draw. Okay, can everybody see that okay?
Yes.
Okay. All right. Batteries, rechargeable batteries, nickel metal hydride, lithium ion, lead acid. Those are all rechargeables. A rechargeable battery means you can reverse the chemical storage by pumping electricity into it. If it's a non-rechargeable battery, that would be called a primary cell, which means that it's non-reversible. You can't do anything with it once it's exhausted. You can try to hook it up backwards and you can't reverse the chemistry. A diode is a one-way device. So what's cool about a diode is that it is a semiconductor made of two different kinds of material. Just erase that. P and N material. The N material has a few extra electrons. The P has a few extra pluses. When you hook it up to a battery, depending on how you hook it up, you'll get current flowing, but if you reverse the battery, you will not. So a silicon diode typically has a voltage drop of 0.7 volts. A germanium diode has a drop of 0.3 volts just to make it work. Essentially, what you have is an anode and a cathode, just like in vacuum tubes. And this is a one-way street. That is the schematic symbol for a diode, an arrow with a bar. And what's interesting about it is that when you go look at one, physically, if you see a diode, it'll be a little black cylinder. It'll have a band on one side, and the banded side is the cathode, which is the negative terminal. If I were to take a diode and do this with it, and I were to draw the AC current, it would look like this, right? The voltage would go up and down and up and down. Everyone agree with that? A diode is a one-way street, and since I don't want to blow my diode up, I want to put a resistor. There we go. Limit the current a little bit. So when the voltage goes positive, the diode will say, okay, one-way street, we're good to go. When the diode goes negative, it'll try to go this way, but notice it's going against the flow. We will not get any flow, which means that what happens is that the waveform that we get over here will look like this. That has a name. What is that called? It's always going one direction. That is called, it's very ugly, but that is called DC, which is direct current. So a diode is the basis for converting AC current or AC voltage into DC. This is known as a rectifier.
That waveform, the pulsating DC that's talked about.
Yep. And this is actually, because it's only operating on half of the wave, this is actually known as a half wave rectifier.
Hey, Scott, I don't know if people noticed, but there was a note put in that 30 more slots were opened.
Oh, or total of 30.
We
Total
opened the
of
exam
30.
session up to 30 applicant
Yeah,
slots.
so total of 30. So 10 more slots.
So is this anything like an inverter?
It could be, except an inverter goes from DC to AC. So okay, so if you wanted to draw an inverter, basically you would do this. So here's, all right. So here's my DC. And my voltage looks like this. Right? Nice flat line. Well, what I can do with this is now I could, for instance, take this DC and instead I could have a switch. Good time to talk about this. A computer controlled switch. A computer controlled switch. So here's my base. This is known as a transistor. Here's my collector. Here's my emitter on my bipolar junction transistor. This is on your test, by the way. Bipolar junction transistor. This is your base, collector, and emitter. By turning this on and off, this is basically an electronic switch. And by doing this, when the base is turned on, it opens this downward path, dropping my power to ground. When it's open, it lets the voltage float high. If I do this periodically, it will do this. It will take my DC and do this with it. Okay, so what does that look like? What kind of wave is that called?
Square wave.
That's called a square wave. Okay, so inside a square wave, this has, depending on what it is, a frequency. I could then take this square wave, because this square wave is actually made of a fundamental, it's made of a, if you go through, I believe it's the Taylor series expansion, it goes through like F3 or plus B, F5, and so on and so forth, where frequency is the basic frequency. This is the third harmonic. This is the fifth harmonic, all the way out to infinity. So by filtering, so let's say that it looks like this. By filtering for just this one frequency, believe it or not, that square wave turns into a sine wave. And notice that it's a sine wave, but it's actually it's a square wave that would be AC, except that it's shifted up. So it's a DC biased sine wave. So I could actually use a low pass filter and an inductor to take out the DC component and then get a sine wave out of it. So that's the basis of an inverter. So, okay, so now we have our diode again. What's a diode? It's a one-way device. So we're going to do this, and we're going to draw a bipolar junction transistor, which is a BJT. I keep doing BJI. Base, collector, and emitter. Notice that this still has that arrow. That looks like a diode. And in fact, a transistor is made of two diodes back to back. That's how it's built. And this right here is known as an NPN. This is a PN diode. This is NPN, and you could actually reverse the arrow, and then it would be PNP. The way that this works is that a small amount of current flowing from the base to the emitter creates a massive amount of current able to flow from the collector to the emitter. So if this is operating in a way that there's a tiny current flowing from the base to the emitter, there'll be a bigger but still tiny-ish current flowing this way down through the collector to the emitter. If we were to make this a big current flowing from the base to the emitter, we'd have a really big current flowing that way. So a bipolar junction transistor can be operated as a switch or as an amplifier, depending on how it's built, depending on how it's biased. So as it turns out, nothing works infinitely well. So a transistor has a curve that kind of looks like this. So you notice this section right here that looks like a straight line? That's known as the linear region of the transistor, where an input will generate a linearly scaled output. This is known as saturation, where no matter how much more you put in, you can't get any more out. And this is known as cutoff, where below this certain point, it doesn't matter how much you put in, you're not getting anything out. So this right here is what we use in semiconductors to turn on ones and zeros. This is the basis for binary logic, storing ones and zeros. This is the basis for amplification, right in there where it's a flat line and it's a slope. There's another type of transistor which looks like this. This is known as a field effect transistor, and it has a gate and a drain and a source. And does anyone see what this kind of looks like right there between the gate and the channel? What does that look like?
Capacitor?
That looks like a capacitor, doesn't it? Now, the thing is, with a bipolar junction transistor, you actually had to put a current into the circuit in order to make it work. If you had a billion of those transistors, a billion times a little amount, it's still quite a bit. So we don't use bipolar junction transistors for semiconductor chips because they would get insanely hot. What we do instead is we take this device, and if we put a voltage right there, which draws no current because we just basically put a charge on the gate plate, that allows the source drain channel to open. And it's either in saturation or linear. It's the exact same thing as with the bipolar transistor, except because there's nowhere for current to flow, these are very, very efficient power ones. And again, this is known as a field effect transistor. And actually, they're used for power, they're used for semiconductors, they're used all over the place. You can put
Is that where the term MOSFET comes from?
That's where MOSFET comes from. Metal oxide. It's just a different substrate. That's where gas FET comes from. That's where IG FET comes from. If you see FET, it all comes from that. Okay, so components of a diode, anode and cathode. There's marked with a stripe. Okay, a light emitting diode is a special diode that puts out light when it's forward biased. When you put voltage into it and it carries current, it emits light. I have a power supply that has a light on it right here behind my table. Sorry, I can't see it from here. When it lights up, that means that the power supply is turned on. Device that can be used as an electronic switch is a transistor. Amplification of a signal. There's that word gain again, the same. And what's another way to measure gain? What's another, what term do we use for that?
dB.
Decibel. Yep, our gain is in decibel. Okay, so 3 regions of semiconductor material is a transistor, bipolar junction transistor, emitter base collector. Good, we covered that. Gate drain source. Okay, that's a FET. Okay, so now we're into practical circuits. Okay, this is a schematic. A schematic from a scheme is basically just a plan, but it's a plan on a piece of paper. It doesn't actually show how it's physically built, it shows how it's wired. So on this drawing right here, number one is what's number one?
Resistor.
Resistor. Number two is a
BJT.
Transistor.
transistor, and in
It's
particular,
a battery.
a bipolar junction transistor. Number two. Number three is a
Light
light
emitting
bulb.
diode.
Or a light bulb. Could be either one.
Lamp.
Number four is a battery. How about number five?
Earth.
Number five is
Ground.
number
Ground.
five is ground. Ground is that any number of different symbols represent ground. Ground is our 0 voltage reference. It doesn't actually have to be 0 volts, but in the case of a circuit, it's our reference for 0 volts. So the way this circuit works is that between number one and that ground going through the transistor, that is one path. And so I know it's right about 1 o'clock. I'm just going to finish up this last section, if that's okay with everyone.
Yeah.
Okay. So here's our transistor. This is path one between the base and the emitter. This is a small current. And this is between the collector and the emitter. This is a very big current. So now let's take a look at that circuit again, and we will see that, wow, that's exactly how it's built. That we have from one, we have the base junction, and we have very low current, but when it's turned on, we get a lot of current going through the light bulb. So when we put a little current on pin number one, the light bulb turns on, powered by the battery. It's an electronic light control switch. This can actually be scaled up to running like, stadium light. Okay, next circuit. Okay, number two is a fuse. Number three is a switch. Number four, anyone know what number four is? That thing looks
Transformer.
right. It looks like two inductors back to back, right? And very briefly, two inductors back to back. They're actually two inductors back to back like this around a common core. So remember, an inductor makes a magnetic field, and it makes a magnetic field going kind of through the core. Well, if we use iron, iron is a ferromagnetic material that contains magnetic fields really well. So if a current makes a magnetic field, or if a current makes a magnetic field, and the magnetic field is in this core going around and around, when it gets to the other coil, that magnetic field will make another current. The proportion, the ratio of turns in the different windings determines what the voltage change is. If I have a 10-to-1 turns ratio and I have 120 volts AC over here, I will get 12 volts AC over here. Pretty cool, right? This is the way to change from one voltage to another by using magnetic fields and inductors. Okay, so what we have here, number four is a transformer. We changed our voltage. How about number five? That's a diode.
Diode.
And what do we know about diodes? They only conduct in what direction?
One way.
One way, in the forward direction, and only when the voltage goes positive. Well, if they only conduct when the voltage goes positive, what we have is we have a voltage that looks like this. That is DC. How about number six? What's number six?
Capacitor.
Right. And since this ugly waveform is really ugly, a capacitor will charge up when it's high and discharge when it's low. So it'll smooth it out. So maybe it'll look like this. And then we have an indicator light, which says the power supply is on. We have a load limiting resistor. And then this is a special diode, which is backwards called, notice it has sort of like a letter Z. This is a Zener diode, which is a voltage reference, which allows us to limit the voltage to a certain point so that instead of being a bumpy line, and we get a lower flat line, and we have a nice half-wave rectified DC power supply. Okay. And next. Okay, so I think the final thing we're gonna do, and I don't know why it's gone gray on me. Okay, then the last one we're gonna do for the day, and then everybody can let their brains relax overnight, is we have one more picture, which is actually quite simple, but very, very profound and has some very serious implications. All right, can everybody see that picture right in the middle? Okay, number 2 is a variable capacitor. The one to the right of it is also a variable capacitor. Number 3 is a variable inductor, and number 4 is an antenna. In the radio world, we deal with something called impedance, right? Impedance is that whole R plus I X thing, where you have two axes. You have the R axis and the X axis up here, and the impedance is like up here. And it actually has an angle, which causes a phase shift and all other cool stuff like that. Well, what it turns out is that we typically want an antenna that has an impedance of 50 ohms purely resisted. Our radio equipment is designed for an impedance of 50 ohms purely resisted. But in the real world, what happens is that this antenna up here might be not 50 ohms, it's something questionable. It's going to be R plus I X. What we can do with this is we take this capacitor and put it in series with the mystery antenna, and then we take that in parallel with this variable inductor, and we then take that in series with this variable capacitor. And by tuning those three things, we can take the impedance, take the reactance part out of it, and tune this so that it looks like 50 ohms. This is known as an antenna tuner. It doesn't solve all your problems, but it's an impedance matching device that basically does magic so that unknown antenna of unknown impedance can be made to work happily with your 50 ohm equipment. Absolute magic. And that is, oh, I'll just do this one thing. This is one more page. And we've already pretty much covered it. Resonant or tuned circuit. If you have an inductor and a capacitor or in series or parallel, that is known as resonant, or a resonant or tuned circuit. What do you use to make a resonant circuit? You use a capacitor and an inductor. Single pole, double throw switch is known as SPDT. That's a single circuit that can go one way or the other way. A relay is an electronically controlled switch, which is a switch combined with an inductor that pulls the circuit in. A meter shows an electrical quantity as a numeric value. A whole bunch of transistors and other components on a single chip is known as an integrated circuit. A regulator controls the amount of voltage from a power supply. So if you have something that is a well-regulated power supply for 13.8 volts, hopefully you'll get 13.8 volts plus just a tiny bit. Your overload protection is known as a fuse, and a reason to use shielded wire. Okay, we talked about current. What does current make? Current flowing makes a magnetic field. And what if you have another wire inside the magnetic field? Those wires will couple together through the magnetic field. So by using a shielded wire, for those of you who have done microphone stuff or audio or studio things, with audio, that's why we use shielded cable on everything to keep signals from cross talking into each other. through magnetic coupling or inductive coupling. Okay. Everybody good for today? I know it's a lot of material.
It's a lot of material.
It's a lot of material. I hope some of it made some sense.
A lot of it did.
Okay, good.
And I'm going to burn through the ham study org as soon as I get off this call. I'm going to start doing the tests,
And I think,
practice test.
and you know, we honestly, we've gone through the really hard stuff. I mean, tomorrow is radio wave propagation and building a station. And then Thursday is going to be how to all the rules and regs and things you can and can't and should and shouldn't do.
I have a question.
Yep.
You said tomorrow is also building a station.
Yep.
I have some stuff. Will that apply to some of my stuff that I bought on eBay? Things like that?
Depends what the stuff is.
I'm sorry?
It depends what the stuff is.
I got an old radio set and things like that from eBay a while back.
It depends what it is. I mean,
okay.
we're gonna learn more about different frequency bands and how they behave. I mean, by virtue of the fact that we've gone through capacitors and inductors, we now know that they're the basis for frequency dependent things. Right? If you use capacitors and inductors together, they can resonate at certain frequencies. And since the source of all of our fun is being able to use different frequencies to our benefit, I mean, that's how we make frequencies, right? That's how we use frequencies. That's how we encode and decode things. Then a lot of it will be, you know, what did you get and what can you listen to and what can you transmit on? And this is, you know, that's why this is kind of like a big old sandbox of stuff.
Right.
And you're learning how to use all the toys in the sandbox.
I'm more of a visual learner, so I wondered if I use my stuff together while I'm listening to you, I might get everything connected in my brain.
That I don't know. That I can't answer.
I have high hopes.
But I have always liked building stuff. I mean, I learned a lot from building. I learned a lot from breaking things.
I'll jump on that wagon.
Yeah. All right, I'm going to stop recording.